So welcome back once again, friends. In last time, in chapter first, we were reading the chapter very slowly, but this time we will not do that thing. We will go ahead faster. Okay. So class 11th NCERT chapter 2, class 11th chemistry, NCERT chapter 2, structure of atom. Objectives. After studying this unit, you will be able to know about the discovery of electron, proton and neutron and their characteristics, describe Thomson-Rutherford and Bohr atomic models, understand the important features of the quantum mechanical model of atom, understand nature of the electromagnetic radiation and Planck's quantum theory, explain the photoelectric effect and describe features of atomic spectra, state the de Broglie relation and Heisenberg uncertainty principle, define an atomic orbital in terms of quantum numbers, state of Bohr principle, Pauli exclusion principle, and Hund's rule of maximum multiplicity, and write the electronic configuration of atoms. Okay, now a quotation is there. The rich diversity of chemical behavior of different elements can be traced to the differences in the internal structure of atoms of these elements. The existence of has been proposed since the time of early Indian and Greek philosophers 400 BC, who were of the view that atoms are the fundamental building blocks of matter. According to them, the continued subdivision of matter would ultimately yield atoms which would not be further divisible. The word atom has been derived from the Greek word atomio, which means uncuttable or non-divisible. These earlier ideas were most speculations, and there was no way to test them experimentally. These ideas remained dormant for very long time, and were revived again by scientists in the 19th century. The atomic theory of matter was first proposed on a firm scientific basis by John Dalton, a British school teacher, in 1808. His theory, called Dalton's atomic theory, regarded the atom as the ultimate particle of matter, unit first. Dalton's atomic theory was able to explain the law of conservation of mass, law of constant proportion, law of constant composition, and law of multiple proportion very successfully. However, it failed to explain the result of many experiments. For example, it was known that substances like glass or ebolite, when rubbed with silk or fur, gets electrically charged. In this unit, we start with the experimental observations made by scientists towards the end of 19th and beginning of 20th century. These established that atoms are made of subatomic particles, that is, electrons, protons, neutrons, a concept of very different from that of Dalton. Page second, 2.1. Discovery of subatomic particles. An insight into the structure of atom was obtained from the experiments on electrical discharge through gases. Before we discuss these results, we need to keep in mind a basic rule regarding the behavior of charged particles. Charged particles repel each other, and unlike charges, attract each other. 2.1.1 Discovery of electron. In 1830, Michael Faraday showed that if electricity is passed through a solution of an electrolyte, chemical reactions occurred at the electrodes, which resulted in the liberation and deposition of matter at the electrodes. He formulated the certain laws which you will study in class 12. These results suggested the particulate nature of electricity. In mid 1850, many scientists, mainly Faraday, began to study electrical discharge in partially evacuated tubes known as cathode ray discharge tubes. It is depicted in figure 2.1. We can see here the same thing in figure 2.1. Okay, now a cathode ray tube is made of glass containing two thin pieces of metal called electrodes sealed in it. The electrical discharge tube, the gases could be observed only at very low pressure and at very high voltages. The pressure of different gases could be adjusted by evacuation of glass tubes. When sufficiently high voltage is applied across the electrodes, current started flowing through a stream of particles moving in the tube from the negative electrode cathode to the positive electrode and node. These were called a cathode ray or cathode ray particles. The flow of current from cathode to anode was further checked by making a hole in the anode and coating the further behind anode with phosphorescent yes phosphorescent material zinc sulfide. When these rays after passing through the anode strike and zinc sulfide coating, a bright spot is developed on the coating, as we can see in figure 2.1b. okay, here we can see the bright light. Figure 2.1b, a cathode ray discharge tube with perforated anode. Observe it, friends, yourself. The results of these experiments are summarized below. First, the cathode rays start from cathode and move towards the anode. These rays themselves are not visible, but their behavior can be observed with the help of certain kind of materials, in bracket fluorescent or phosphorescent, which glow when hit by them. Television picture tubes are cathode ray tubes, and television picture results due to the fluorescence of on the television screen coated with certain fluorescent or photorescent materials. Third, in the absence of electrical or magnetic field, these rays travel in straight lines. Figure 2.2. Where is figure 2.2? Here is figure 2.2. Okay. See, there is figure 2.2. Now we were here. In the absence of third, we were studying third. In the absence of electric or magnetic field, these rays travel in straight line. Figure 2.2. In the presence of electric or magnetic field, the behavior of cathode rays are similar to that expected from negative charged particles, suggested that the cathode uh, rays are similar to that of fourth point. In the presence of electrical or magnetic field, the behavior of cathode rays are similar to that expected from negatively charged particles, suggesting that the cathode rays consist of negatively charged particles called electrons. Fifth, the characteristics of cathode rays, in bracket electrons, do not depend upon the material of electrodes and the nature of the gas present in the cathode ray tube. Thus, we can conclude that electrons are basic constituent of all the atoms. We are on the 31st number page. 2.1.2, charge to mass ratio of electron. In 1897, British physicist J.J. Thomson measured the ratio of electrical charge E to the mass of electron ME by using cathode ray tube and applying electrical and magnetic field perpendicular to each other as well as to the path of electrons in figure 2.2. Yes, we have showed that in figure 2.2. Now, when only electric field is applied, the electrons deviate from their path and hit the cathode ray tube at point A, figure 2.2. Similarly, when only magnetic field is applied, electron strikes the cathode ray tube at point C. By carefully balancing the electrical and magnetic field strength, it is possible to bring back the electron to the path which is followed in the absence of electrical or magnetic field, and they hit the screen at point B. Thomson argued that the amount of deviation of the particles from their path in the presence of electrical or magnetic field. First, the magnitude of the negative charge of the particle, greater the magnitude of the charge of the particle, greater is the interaction with the electric or magnetic field, and thus greater is the deflection. Second, the mass of the particle, lighter the particle, greater the deflection. Now the third, the strength of the electrical and magnetic field, the deflection of electrons from its original path increases when with the increase in the voltage across the electrodes or the strength of the magnetic field. By carrying out accurate measurements on the amount of deflections observed on the electrons on the electric field strength or magnetic field strength, Thomson was able to determine the value of E by ME as E by ME is equal to 1.758820 into 10 to the power 11 coulomb per kg, where m is the mass of electron in kg and E is the magnitude of the charge on the electron in coulomb C. Since electrons are negatively charged, the charge on the electron is minus E. 2.1.3, charge on the electron. R.A. Millikan lived from 1868 to 1953 devised a method known as oil drop experiment, and in bracket 1906 to 1914 to determine the charge on the electrons. He found the charge on the electron to be minus 1.6 into 10 to the power minus 19 coulomb. The present accepted value of the electric charge is minus 1.602176 into 10 to the power minus 19 coulomb. The mass of the electron Me was determined by the combining these results with Thomson's value of E by Me ratio. Me is equal to E by Me is equal to 1.602176 into 10 to the power minus 19 coulomb by 1.758820 into 10 to the power 11 coulomb per kg, gives finally 9.1094 into 10 to the power minus 31 kg. As we can, this is equation 2.2. Here we can observe figure 2.2, cathode and node, and it is passing through relatively perpendicular these electrical and magnetic fields, and it is just tracking on the other side on the fluorescent ABC points. Okay, now page number 32, 2.1.4, discovery of protons and neutrons. Electrical discharge carried out in the modified cathode ray tube led to discovery of canal rays carrying positively charged particles. The characteristics of these positively charged particles are listed below. First, unlike cathode rays, mass of positively charged particles depends upon the nature of gas present in the cathode ray tube. These are simply the positively charged gaseous ions. Second, the charge to mass ratio of the particles depends on the gas from which these originate. Third, some of the positively charged particles carry a multiple of the fundamental unit of electrical charge. Fourth, the behavior of these particles in the magnetic or electric field is opposite to that observed for electric or electron or cathode rays. The smallest and the lightest positive ion was observed from hydrogen and was called proton. The positively charged particle was characterized in 1919. Later, a need was felt for the presence of electrically neutral particle as one of the constituent of atom. These particles were discovered by Chadwick in 1932 by bombarding a thin sheet of beryllium by alpha particles. When electrically neutral particles having a mass slightly greater than that of protons were emitted, he named these particles as neutrons. The important properties of all these fundamental particles are given in table 2.1. Where is table 2.1? Yes, here is table 2.1, properties of fundamental particles. Okay, now here 2.2, atomic models. Observations obtained from the experiments mentioned in the previous sections have suggested that Dalton's indivisible atom is composed of subatomic particles carrying positive and negative charges. The major problem before the scientists after the discovery of subatomic particles were, uh, first, to account for the stability of atoms; second, to compare the behavior of elements in terms of both physical and chemical properties. Here one explanation of Millikan's oil drop method is there. In this method, oil droplets in the form of mist produced by the atomizer were allowed to enter through a tiny hole in the upper plate of electrical condenser. The downward motion of these droplets was viewed through the telescope equipped with a micrometer eyepiece. By measuring the rate of fall of these droplets, Millikan was able to measure the mass of oil droplets. The air inside the chamber was ionized by passing a beam of X-rays through it. The electrical charge on these oil droplets were acquired by collisions with gaseous ions. The fall of these charged oil droplets can be regarded, accelerated, retarded, accelerated, or made stationary depending upon the charge on the droplets and the polarity and strength of the voltage applied to the plate. By carefully measuring the effects of electrical field strength on the motion of oil droplets, Millikan concluded that magnitude of the electrical charge Q on the droplets is always an integral multiple of the electrical charge E. that is Q is equal to Ne, where N is equal to 1, 2, 3 dash dash dash. Here is the figure of 2.3. The Millikan oil drop apparatus for the measuring charge E in the chamber. Forces acting on oil drop are gravitational, electrostatic due to electrical field, and a viscous drag force when the oil drop is moving. Here you can observe the apparatus. Okay, so we were here in atomic models in the last paragraph. Okay, after 2 points, here is the two more points. The major problems before the scientists after the discovery of the subatomic particles were to account for the stability of atom, to compare the behavior of elements in terms of both physical and chemical properties, to explain the formation of different kinds of molecules by combination of different atoms, and to understand the origin and nature of the characteristics and electromagnetic radiation absorbed or emitted by atoms. Now page number 33, properties of fundamental particles. This is given in table 2.1. Names of the particles are electron, proton, neutron. Symbols are respectively E, P, N for electron, proton, neutron, and absolute charges are for electron minus 1.62602.176 into 10 to the power minus 19. Its relative charge is minus 1. Mass per kg value is 9.109382 into 10 to the power minus 31. Mass by U value is 0.00054. Approx mass by U value is 0. For proton, the absolute charge is plus the same as that of electron. The relative charge is plus 1 while the electron was minus 1. The mass by kg value is different from the electron, and that is 1.67262216 into 10 to the power minus 27. Mass by U value is also different for proton, and it is 1.00727, and approx mass by U value is 1. For neutron, the absolute charge by C value is 0, the relative charge value is 0, mass by kg value is 1.674927 into the power minus 27, and just nearly equal to that of proton but a little bit different. And mass by U value is 1.00867, again nearly equal to proton, and it approx mass by U value is just same as proton, that is 1. Okay, different atomic models were proposed to explain the distributions of these charged particles in an atom. Although some of these models were not able to explain the stability of atoms, though two of these models, one proposed by J.J. Thomson and other proposed by Ernest Rutherford, are discussed below. 2.2.1 Thomson model of atom. J.J. Thomson in 1898 proposed that an atom possesses a spherical J.J. Thomson in 1898 proposed that an atom possesses a spherical shape in bracket radius approximately 10 to the power minus 10 meter, in which the positive charge is uniformly distributed. The electrons are embedded in it in such a manner as to give the most stable electrostatic arrangement. Figure 2.4 Thomson model of atom. Many different names are given to this model. For example, plum pudding, raisin pudding, or watermelon. This model can be visualized as the pudding or watermelon of positive charge with plums or seeds electrons embedded into it. An important feature of this model is that the mass of the atom is assumed to be uniformly distributed over the atom. Although this model was able to explain the overall neutrality of the atom but was not consistent with the results of later experiments, Thomson was awarded Nobel Prize for Physics in 1906 for his theoretical and experimental investigations on the conduction of electricity by gases. In the later half of the 19th century, different kinds of rays were discovered. Besides those mentioned earlier, Wilhelm Röntgen from 1845 to 1923 in 1895 showed that when electrons strike a material in the cathode ray tubes, produce rays which can cause fluorescence in the fluorescent materials placed outside the cathode ray tubes. Since Roentgen did not know the nature of the radiation, he named the X-rays, and name is still carried on. It was noticed that X-rays are produced effectively when electrons strike the dense metal anode called targets. These are not deflected by the electric and magnetic fields and have a very high penetrating power through the matter, and this is the reason that these rays are used to study interior of the objects. These rays are very short wavelengths, approximately 0.1 nanometer, and possess electromagnetic character. Section 2.3.1. Okay, we will see in the section 2.3.1. Where is that section? 2.3. Okay, we will study it later. Now, Henri Becquerel from 1852 to 1908 observed that there are certain elements which emit radiation on their own and named this phenomenon as radioactivity, and the elements known as radioactive elements. This field was developed by Marie Curie, Pierre Curie, Rutherford, and Frederick Soddy. It was observed that three kinds of rays, that is alpha, beta, and gamma, are emitted. Rutherford found that alpha rays consist of high energy particles carrying 2 units of positive charge and 4 units of atomic mass. He concluded that alpha particles are helium nuclei, as when alpha particles combined with 2 electrons yielded helium gas. Beta rays are negatively charged particles similar to the electrons. The gamma rays are very high energy radiations like X rays, are neutral in nature and do not consist of particles as regarded penetrating power. Alpha particles are the least, followed by beta rays 100 times that of alpha particles, and gamma rays 1000 times that of alpha particles. 2.2.2. Rutherford's nuclear model of atom. Rutherford and his students Hans Geiger and Ernest Marsden bombarded very thin gold foil with alpha particles. Rutherford's famous alpha particle experiment is okay, this is shown in figure as follows. Okay, Rutherford's famous alpha particle scattering experiment is represented in figure 2.5. Yes, we can see that here. A stream of high energy alpha particle from a radioactive source was directed at a thin foil thickness approximately equal to 100 nanometer of the gold metal. The thin gold foil had a circular fluorescent zinc material around it. Whenever alpha particles struck on the screen, a teeny flash of light was produced at that point. The results of scattering experiment were quite unexpected. According to Thomson model of atom, the mass of each gold atom in the foil should have According to the Thomson model of atom, the mass of each gold atom in the foil should have spread evenly over the entire room, and alpha particles had enough energy to pass directly through such a uniform distribution of mass. It was expected that the particles would slow down and change the direction only by small angles as they pass through the foil. It was observed that first, most of the alpha particles pass through the gold foil undeflected. Second, a small fraction of alpha particles was reflected by small angles. Third, a very few alpha particles, nearly equal to 1 in 2000, bounced back, that is, were reflected by nearly 180 degree. On the basis of the observations, Rutherford drew the following conclusions regarding the structure of atom. Most of the space in atom is empty, as most of the alpha particles pass through the foil undeflected. Second, a few positively charged alpha particles were deflected. The deflection must be due to the enormous repulsive force, showing that the positive charge of atom is not split throughout the atom as Thomson had presumed, the positive charge has to be concentrated in a very small volume that repelled and reflected the positively charged alpha particles. Third, the calculations by Rutherford show that the volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. The radius of the atom is about 10 to the power minus 10 meter, while that of nucleus is 10 to the power minus 15 meter. One can appreciate this difference in size by realizing that if a cricket ball represents a nucleus, then the radius of the atom would be about 5 kilometer. We are on the 35th number page. On the basis of above observations and conclusions, Rutherford proposed the nuclear model of atom. According to this model, first, the positive charge and most of the mass of the atom was densely concentrated in an extremely small region. This very small portion of the atom was called nucleus by Rutherford. The nucleus is surrounded by electrons that move around the nucleus with a very high speed in circular path called orbits. Thus, Rutherford's model of atom resembles the solar system, in which nucleus plays the role of sun and the electrons that of revolving planets. Third, electrons and the nucleus are held together by electrostatic forces of attraction. 2.2.3, the atom and the mass number, atomic number and mass number. The presence of positive charge on the nucleus is due to the presence of positive charge on the nucleus is due to the protons in the nucleus. As established earlier, the charge on the proton is equal but opposite to that of electron. The number of proton present in nucleus is equal to atomic number in bracket Z. For example, the number of protons in the hydrogen nucleus is 1. In sodium atom it is 11, and their atomic numbers are 1 and 11 respectively. In order to keep the electrical neutrality, the number of electrons in an atom is equal to the number of protons in bracket atomic number Z. For example, number of electrons in hydrogen atom and sodium atom are 1 and 11 respectively. Atomic number in bracket Z is equal to number of protons in the nucleus of an atom is equal to number of electrons in an atom. Number of electrons in a neutral atom. Okay, this is 2.3. While the positive charge of the nucleus is due to the protons, the mass of nucleus due to the protons and neutrons. As discussed earlier, protons and neutrons present in the nucleus are collectively known as nucleons. The total number of nucleons is termed as mass number A of the atom. Mass number A is equal to mass of protons plus mass of neutrons. This is equation 2.4. 2.2.4 Isobars and isotopes. The composition of any atom can be represented by using the normal element symbol X with superscript on the left hand side as the atomic mass number A and subscript Z on the left hand side as the atomic number. That is, A as the left hand side superscript of X and Z as the left hand side subscript of X. Okay, now isobars are the atoms with same mass number but different atomic number. For example, 14 C6 and 14N7. On the other hand, atoms with identical atomic number but different atomic mass are known as isotopes. In other words, according to the equation 2.4, it is evident that difference between the isotopes is due to the presence of different number of neutrons present in nucleus. For example, considering of hydrogen atom again, 19.985% of hydrogen atom contain only one proton. This isotope is called protium, 11H. Rest of the percent of hydrogen atom contains two other isotopes. The one containing one proton and one neutron is called deuterium 21D, 0.015%, and the other one possessing one proton and two neutrons is called tritium 31T, as subscript and superscript and subscript respectively. The latter isotope is found in trace amounts on the earth. The other examples of commonly occurring isotopes are carbon atom containing 6, 7 and 8 neutrons besides 6 protons, 12, 6C, 13, 6C, 14, 6C. Chlorine atom containing 18 and 20 neutrons besides 17 protons, 35, 17 chlorine, 37, 17 chlorine. Lastly, an important point to mention regarding isotopes is that chemical properties of atoms are controlled by the number of electrons, which are determined by the number of protons in the nucleus. By the कुछ गलत तो पढ़ दिया क्या? अच्छा, फिर से पढ़ता हूँ. Lastly, an important point to mention regarding isotopes is that chemical properties of atoms are controlled by the number of electrons, which are determined by the number of protons in nucleus. Number of neutrons present in the nucleus have very little effect on the chemical properties of an element. Therefore, all the isotopes of an given element show some chemical behavior. Problem 2.1 is there, which is calculate the number of protons, neutrons and electrons in 8035 bromine. Solution: in this case 8035 bromine, Z is equals to 35, A is equal to 80, species is neutral, number of protons is equal to number of electrons is equal to Z equal to 35, number of neutrons is equal to 80, minus 35 is equal to 45 from equation 2.4. Problem number 2.2, the number of electrons and protons and neutrons in a species are equal to 18, 16 and 16 respectively. Assign the proper symbol to the species. Solution: the atomic number is equal to the number of protons is equal to 16. The element is sulfur. S. Atomic mass number is equal to number of protons plus number of neutrons is equal to 16 plus 16 is equal to 32. Species is not neutral as the number of protons is not equal to electrons. It is anion, negatively charged, with charge equal to excess electrons is equal to 18 minus 16 is equal to 2. Symbol is 32 as superscript, 16 as subscript of S2 minus. Note before using the notation subscript A, superscript A is subscript Z of X. Find out whether the species is a neutral atom, an ion, a cation or an anion. If it is a neutral atom, equation 2.3 is valid. What is equation 2.3? Let's review here. Yes, this is 2.3. And if the species is an ion, determine whether the number of protons are larger, cation, positive ion, or smaller, in bracket anion or negative ion, than the number of electrons. Number of neutrons is always given by A to Z, whether the species is neutral or ion. 2.2.5 Drawbacks of the Rutherford model. As you have learnt about, Rutherford nuclear model of an atom is like a small scale solar system with the nucleus playing the role of massive sun and the electrons being similar to the lighter planets. When classical mechanics is applied to the solar system, it shows that the planets describe well-defined orbits around the sun. The gravitational force between the planets is given by the expression G.m1m2 by r square, where m1 and m2 are the masses, r is the distance of separation of the masses, and g is the gravitational constant. The theory can calculate precisely the planetary orbits, and these are in agreement with the experimental measurements. The similarity between the solar system and the nuclear model suggests that electrons should move around the nucleus in a well-defined orbits. Further, the Coulomb force k q1 q2 by r square, where q and q2 are charges, r is the distance of separation of the charges, and k is the proportionality constant between electron and nucleus, is mathematically similar to the gravitational force. However, when a body is moving in an orbit, it undergoes acceleration even if it is moving with a constant speed in an orbit because of the changing direction. So, an electron in the nuclear model describing planet-like orbits is under acceleration. According to the electromagnetic theory of Maxwell, charged particles when accelerated should emit electromagnetic radiation. In bracket, this feature does not exist for planets since they are unchanged or charged. Therefore, an electron in an orbit will emit radiation. The energy carried by radiation comes from electronic motion. The orbit will thus continue to shrink. Calculations show that this should take an electron only 10 to the power minus 8 seconds to spiral into the nucleus, but this does not happen. Thus, the Rutherford model cannot explain the stability of atom. If the motion of an atom is described on the basis of the classical mechanics and electromagnetic theory, you may ask that since the motion of electrons in orbits is leading to the instability of the atom, then why not consider electrons as stationary around the nucleus? If the electrons were stationary, electrostatic attraction between the dense nucleus and the electron would pull the electrons electrons would pull the electron towards the nucleus to form a miniature version of Thomson model of atom. Another serious drawback of the Rutherford model is that it says nothing about the distribution of electrons around the nucleus and energies of these electrons. Okay, in the last page we have left lowermost portion surrounded by this red sign, and that is the star point. Classical mechanics is a theoretical science based on Newton's law of motion. Sorry. Classical mechanics is a theoretical science based on Newton's law of motion. It specifies the law of motion of macroscopic objects. Okay, we were here. 2.3 Developments leading to the Bohr model of atom. Historically, results observed from the studies of interactions of radiations with matter have provided immense information regarding the structure of atom and molecules. Niels Bohr utilized these results to improve upon the model proposed by Rutherford. Two developments played a major role in the formulation of Bohr model of atom. These were: first, dual character of electromagnetic radiation, which means the radiations possess both wave-like and particle-like properties, and second, experimental results regarding atomic spectra. First, we will discuss about the dual nature of electromagnetic radiations. Experimental results regarding atomic spectra will be discussed in section 2.4. 2.3.1 Wave nature of electromagnetic radiation. In the mid-19th century, physicists actively studied absorption and emission of radiation by heating objects. These are called thermal radiations. They try to find out what the thermal radiations is made. It is now a well-known fact that thermal radiations consist of electromagnetic waves of various frequencies or wavelengths. It is based on a number of modern concepts which were unknown in the mid-19th century. First active study of thermal radiation laws occurred in 1850s, and theory of electromagnetic waves and the emission of such waves by accelerating charged particles was developed in the early 1870s by James Clerk Maxwell, which was experimentally confirmed later by Henri Becquerel. Here we will learn some facts about the electromagnetic radiations. James Maxwell 1870 was the first to give a comprehensive explanation about the interaction between the charged bodies and their behavior of the electrical and magnetic fields on microscopic level. He suggested that when Electrically charged particle moves under acceleration, alternating current and magnetic fields are produced and transmitted. These fields are transmitted in form of waves called electromagnetic waves or electromagnetic radiation. Light is the form of radiation known from earlier days, and speculation about its nature date back to remote ancient times. In earlier days, Newton light was supposed to be made of particles, corpuscles. It was only in the 19th century when wave nature of light was established. Maxwell was again the first to reveal the light waves are associated with oscillating electrical and magnetic character, figure 2.6. Figure 2.6 electrical and magnetic field components of electromagnetic wave. These components have the same wavelength, frequency, speed and amplitude, but they vibrate in two mutually perpendicular planes. Okay, friends, observe yourself this figure. Okay, in this figure we can see that the electromagnetic field component is shown as the vertical, and magnetic field component is shown in a blue color, and it is horizontal, and the direction of propagation of both of these is just perpendicular to both these electric field and magnetic field. Okay, although although electromagnetic wave motion Although electromagnetic wave motion is complex in nature, we will consider here only a few simple properties. First, the oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other, and both are perpendicular to the direction of the propagation of the wave. Simplified picture of electromagnetic wave is shown in figure 2.6. Okay, simplified picture of is shown in figure 2.6. Oh, this was the 2.6. We have already observed that in this. Okay, so second, unlike sound waves or waves produced in water, electromagnetic waves do not require medium and can move in vacuum. Third, it is now well established that there are many types of electromagnetic radiations which differ from one another in wavelength or frequency. These constitute what is called electromagnetic spectrum. Figure 2.7 shows this electromagnetic spectrum. We can see here A, B, and figure 2.7. Okay, we will discuss, we will come here later. Okay, after figure 2.7, different regions of the spectrum are identified by different names. Simple. Some examples are radio frequency region around 10 to the power 6 Hz used for broadcasting, microwave region around 10 to the power 10 Hz used for radar, infrared region around 10 to the power 13 Hz used for heating, ultraviolet region around 10 to the power 16 Hz, component of sun's radiation. The small portion around 10 to the power 15 Hz is what the ordinary called visible light. It is only this part which our eyes can see or detect. Special instruments are required to detect non-visible radiation. Fifth, different kinds of units are used to represent electromagnetic radiation. These radiations are characterized by properties, namely frequency in bracket nu, this is read as nu, frequency is depicted as nu, and wavelength lambda. Okay, the SI unit of frequency nu is hertz hertz per second, and after Henrich hertz. The SI unit of frequency nu is hertz per second after Henrich hertz. It is defined as the number of waves that pass a given point in a 1 second. Wavelength should have units of length. As you know, the SI unit of length is meter. Since electromagnetic radiation consists of different kinds of waves of different Since electromagnetic radiation consists of different kinds of waves of much smaller wavelengths, smaller units are used. Figure 2.7 shows various types of electromagnetic radiations which differ from one another in wavelengths and frequencies. In vacuum, all types of electromagnetic radiation, regardless of wavelength, travel at the same speed, that is 3.0 into 10 to the power 8 meter per second, accurately in bracket 2.997925 into 10 to the power 8 meter per second to be precise. This is called speed of light, and is given in and is given the symbol C. The frequency nu, wavelength lambda, and the velocity of light c are related by the equation 2.5, and that is c is equal to nu lambda. Okay, here in A is a strip that is simply showing the variation of frequency and variation of wavelength relatively. The range of the frequency, as we can see, that is from 10 to the power 24 to 10 to the power 0, means 10 to 24, 10 to 10 to 10 to 10 to the power 24, and the range of wavelength varies between 10 to the power minus 16 to 10 to the power 8. Okay, and here there is a, yes, here in the B portion we can see visible spectrum that is between that is just around 10 to the power 15 frequency hertz. Okay, figure 2.7 A, spectrum of electromagnetic radiation. B, visible spectrum. The visible region is only small part of the entire spectrum. Okay, understand this by yourself. My job is just to read. Okay, understand by yourself, you will understand. चिंता करने की बात नहीं है. चलो, okay, 39 page. The other commonly used quantity, especially is spectroscopy, is the wave number nu bar. The other commonly used quantity, especially in spectroscopy, is the wave number, that is represented as nu bar. It is defined as the number of wavelengths per unit length. Its units are reciprocal of wavelength unit, that is per meter. However, commonly used unit is per centimeter. Not this is it should be noted that this is not, per centimeter is not a SI unit. Okay, problem 2.3. The Vivid Bharati station of All India Radio Delhi broadcasts on a frequency of 1368 kilohertz. Calculate the wavelength of electromagnetic radiation emitted by the transmitter. Which part of electromagnetic spectrum does it belong to? Okay, it has solution. The wavelength lambda is equal to c by nu, where c is the speed of electromagnetic radiation in vacuum and nu is the frequency. Substituting the given values, we have lambda is equal to c by nu is equal to 3.00 into 10 to the power 8 meter per second by 1368 kilohertz. The frequency from which the Vivid Bharati broadcasts is equal to 3.00 into 10 to the power 8 meter per second by 1368 into 10 to the power 3 per second is equal to 219.3 meter. This is the characteristic radio wave wavelength. Problem 2.4. The wavelength range of the visible spectrum extends from violet in bracket 400 nanometer to red, that is 750 nanometer. Express these wavelengths in frequencies, that is hertz. Note that 1 nanometer is equal to 10 to the power minus 9 meter. Solution. Using equation 2.5. What was the equation 2.5? Do you remember it? Here. Okay, just before the spectrum strip, c is equal to nu lambda. c is equal to nu lambda. ओके, देखिए कौन सा चीज़ पेज के किस पोर्शन पे दिया हुआ है, ये चीज़ जानना ज़रूरी है. इसीलिए मैं कहता हूँ कि आप लोग अपनी किताब के साथ में और पेंसिल ले करके बैठा करें. ठीक है, यही इम्पोर्टेंस है और यही कारण है कि मैं सिर्फ ऑडियो ना बना के ये फ़ोटो के साथ में, कंटेंट के साथ में उसको ये रिकॉर्ड कर रहा हूँ वॉइस. ओके, तो हमें पता होना चाहिए कौन चीज़ कहाँ पे है ताकि जल्दी हम रेफ़र कर सकें. इसीलिए मैं चीज़ें आने पर मैं वहाँ पे ड्रैग कर रहा हूँ अपना स्क्रीन. चलिए, ठीक है. सॉल्यूशन. यूजिंग इक्वेशन 2.5 फ्रिक्वेंसी ऑफ वॉयलेट लाइट. यूजिंग इक्वेशन 2.5 दिखा दिया. इक्वेशन कहाँ पे था, क्या था, c इज इक्वल टू न्यू लैम्डा. तो यूजिंग 2.5 frequency of violet light Nu is equal to C by lambda 3.00 into 10 to the power 8 meter per second by 400 into 10 to the power minus 9 meter is equal to 7.50 into 10 to the power 14 hertz. Okay. Frequency of red light nu is equal to C by lambda is equal to 3.00 into 10 to the power 8 meter per second by 750 into 10 to the power minus 9 meter is equal to 4.00 into 10 to the power 14 hertz. The range of visible spectrum is from 4.0 into 10 to the power 14 to 7.5 into 10 to the power 14 hertz in terms of frequency units. Problem 2.5, calculate A, wave number, and B, frequency of yellow radiation having wavelength 1500 angstrom. This is the symbol of angstrom. Solution A, calculation of wave number nu bar, calculation of wave number in bracket nu bar. Lambda is equal to 1500, 5800 angstrom is equal to 5800 and 10 to the power minus 8 centimeter is equal to 5800 into 10 to the power minus 10 meter. Nu bar is equal to 1 by lambda is equal to 1 by 5800 into 10 to the power minus 10 meter is equal to 1.724 into 10 to the power 6 per meter, means meter to the power minus 1 is equal to 1.724 into 10 to the power 4 centimeter per centimeter. B, calculation of frequency nu bar is equal to C by lambda is equal to 3 into 10 to the power 8 meter per second by 5800 into 10 to the power minus 10 meter is equal to 5.172 into 10 to the power 14 per second. 2.3.2, particle nature of electromagnetic radiation, that is Planck's quantum theory. Again, particle nature of electromagnetic radiation, that is Planck's quantum theory. Some of the experimental phenomena such as diffraction and interference, some of the experimental phenomena such as diffraction and interference can be explained by the wave nature of the electromagnetic radiation. However, following are some of the observations which could not be explained with the help of even of the electromagnetic theory of 19th century physics known as classical physics. First, the nature of emission of radiation from hot bodies in bracket blackbody radiation. Second, ejection of electrons from metal surface when radiation strikes it in bracket photoelectric effect. Third, variation of heat capacity of solids as a function of temperature. Okay, here as a start point, single start point and second double start point, diffraction and interference. The both definitions are given in the boundary of red line on the bottom of page. Okay, see here, single star says that diffraction is the bending of wave around an obstacle. किसी चीज पे रुक के डिफ्रैक्शन जो वेव बेंड हो जाता है उसको डिफ्रैक्शन बोलते हैं. एंड डबल स्टार रिप्रेजेंट्स दैट इंटरफेरेंस इज द कॉम्बिनेशन ऑफ टू वेव्स ऑफ द सेम or different frequencies to give a wave whose distribution as each point in space is the algebraic or vector sum of disturbances at the point resulting from each interfering wave. बहुत लंबा है, खैर पता नहीं. Now fourth, line spectra of atom with special reference to hydrogen. This phenomenon indicates that the system can take energy only in discrete amounts. All the possible energies can be taken up or radiated. It is noteworthy that the first concrete explanation for the phenomenon of the blackbody radiation mentioned above was given by Max Planck in 1900. Let us first try to understand this phenomenon, which is given below. Hot objects emit electromagnetic radiations over a wide range of wavelengths at high temperatures. An appreciable portion of radiation is the visible region of the spectrum. As the temperature is raised, a higher proportion of short wavelength blue light is generated. For example, when an iron rod is heated in a furnace, it first turns to dull red and then progressively becomes more and more red as the temperature increases. As this is heated further, the radiation emitted becomes white and then becomes blue as the temperature becomes very high. This means that red radiation is the most intense at a particular temperature and the blue radiation is the more intense at another temperature. This means intensities of radiations of different wavelengths emitted by hot body depend upon its temperature. By late 1850s, it was known that objects made of different material kept at different temperatures emit different amount of radiation. Also, when the surface of objects is irradiated with light, electromagnetic radiation, a part of radiant energy is generally reflected. As such, a part is observed and a part of it is transmitted. The reason for incomplete absorption is the ordinary objects at the reason for incomplete absorption is that ordinary objects are as a rule imperfect observers of radiation. An ideal body which emits and absorbs radiation of all frequencies uniformly is called a black body, and radiation emitted by such a body is called blackbody radiation. In practice, no such bodies exist. Carbon black approximately Carbon black approximates fairly close to black body. A good physical approximation of black body is a cavity with a tiny hole which has no other opening. Any ray entering the hole will be reflected by the cavity walls and will be eventually absorbed by the walls. A wall body is also a perfect radiator of radiant energy. Further sum, a black body is in thermal equilibrium with its surroundings. It radiates some amount of energy per unit area as it absorbs from its surroundings in any given time. The amount of light emitted in bracket intensity of radiation from a black body and its spectral distribution depends only on its temperature. At a given temperature, intensity of radiation emitted increases with the increase of wavelength, reaches a maximum value at a given wavelength and then starts decreasing with further increase of wavelength as shown in figure 2.8. okay, this is 2.8. Also, as the temperature increases, maxima of curve shifts to short wavelength. Several attempts were made to predict the intensity of radiation as a function of wavelength, but the results of the above experiments could not be explained satisfactorily on the basis of the wave theory of light. Max Planck, this is the figure 2.8, wave intensity relationship. In the red line we can see that as the intensity is increasing, wavelength is also increasing, and at a certain point of intensity, after that the wavelength start decreasing, and the same is happening with the T1 temperature also, as the blue line is showing. And here at the top, under this square, T2 is greater than T1. okay, and this is figure 2.8a, black body, how the radiations are stacking from one wall to another and then stacking back. This is shown in this. So we were here, but the results of the above experiment could not be explained satisfactorily on the basis of the wave theory of light. Max Planck arrived at a satisfactory relationship by making an assumption that absorption and emission of radiation arises from oscillator, that is, atom in the wall of black body. Their frequency of oscillation is changed by interaction with oscillators of electromagnetic radiation. Planck assumed that radiation could be subdivided into discrete chunks of energy. He suggested that atoms and molecules could emit or absorb only in discrete quantities and not in continuous manner. He gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. the energy E of a quantum of radiation is proportional to its frequency in bracket nu and is expressed by the equation 2.6. E is equal to h nu. The proportionality constant h is also known as Planck's constant and has the value of 6.626 into 10 to the power minus 34 जूल सेकेंड. और रेजोनेंस में हमारे टीचर इसको बड़े इंटरेस्टिंग ढंग से बोलते थे, थोड़ा सा हंसा के, ठीक है. डबल मीनिंग है, छक्का पॉइंट छक्का तो छक्का इंटू 10 टू द पावर माइनस 34 पढ़ा है, मतलब याद है. चलिए ठीक है. छक्का पॉइंट छक्का तो छक्का इंटू 10 टू द पावर माइनस 34 समझ में आया ना. छक्का पॉइंट छक्का तो छक्का. चलिए चलिए ठीक है. और 10 टू द पावर माइनस 34 ये भी आज तक नहीं भूल पाया मैं, कोई हम में से नहीं भूलेगा. ठीक है चलिए. विद दिस थ्योरी Planck was able to explain the distribution of intensity in the radiation from black body as a function of frequency or wavelength at different temperatures. Once again, with this theory, Planck was able to explain the distribution of intensity in the radiation from black body as a function of frequency and wavelength at different temperatures. Quantization has been compared to standing on a staircase. A person can stand only any on any step of a staircase, but it is not possible for him to stand in between the two steps. This energy can take only the values from the following set but cannot take on any values between them. E is equal to 0 h nu, 2 h nu, 3 h nu, dash 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 n h nu. That means 2 point not, it can take 2.5, 3.5 or something. Okay, it will take only a whole numbers. Okay, this is figure 2.9 showing something we have not reached here. Okay, see, Max Planck about something. Max Planck, a German physicist, received his PhD in theoretical physics from the University of Munich in 1879. In 1888, he was appointed director of Institute of Theoretical Physics at the University of Berlin. Planck was awarded the Nobel Prize in Physics in 1918 for his quantum theory. Planck also made significant contributions in thermodynamics and other areas of physics. So versatile, so nice, great. Okay, he lived from 1858 to 1947. हाँ, the year भारत आज़ाद हुआ 1947 में मरे. अरे सेलिब्रेट करने आना चाहिए आपको. हाँ, लेकिन मर गए आप, क्यों बददुआ लग गई, इतना कुछ पढ़ाने के लिए आप छोड़ गए हैं. खैर मजाक है, इन्हीं की वजह से अभी बहुत कुछ हमें मिला है. खैर, photoelectric effect. In 1887, H. Hertz performed a very interesting experiment in which electrons or electric current were ejected when certain metals, for example potassium, rubidium, cesium, etc., were exposed to a beam of light as shown in figure 2.9. हाँ, अब 2.9 की बात आई है. ये कह रहा है कि एक क्या कहते हैं, शायद वैक्यूम है. ये एक ट्यूब के अंदर में कुछ रखा हुआ है. हाँ, एक मेटल सरफेस है और इस पर लाइट जब कर रहा है तो रिफ्लेक्ट होके और ये डिटेक्टर पे इलेक्ट्रॉन का स्ट्राइक हो रहा है, और जिससे आम मीटर में, यहाँ देख रहे हैं ना, आम मीटर में कुछ ना कुछ डिफ्लेक्शन हो रहा है, जिससे कि पता चल रहा है इलेक्ट्रिसिटी कहीं ना कहीं प्रोड्यूस हुई है. फिगर 2.9. इक्विपमेंट फॉर स्टडिंग द फोटोइलेक्ट्रिक इफेक्ट लाइट ऑफ अ पार्टिकुलर फ्रीक्वेंसी स्ट्राइक्स अ clean metal surface inside a vacuum chamber. Electrons are ejected from the metal and are counted by detector that measures their kinetic energy. Okay, so we were here, were exposed to a beam of light as shown in figure 2.9. The phenomenon is called photoelectric effect. What is called photoelectric effect? In 1887, H. Hertz performed a very interesting experiment in which electrons or electric current were ejected when certain metals, for example potassium, rubidium, cesium, etc., were exposed to a beam of light as shown in figure 2.9. The phenomenon is called photoelectric effect. Okay, understood. The result observed in this experiment were: first, the electrons are ejected from the metal surface as shown in figure first, the electron are ejected from the metal surface as soon as the beam of light strikes the surface. That is, there is no time lag between the striking of beam and the ejection of electrons from the metal surface. Second, the number of electrons ejected is proportional to the light or brightness of the light. Third, to the intensity and brightness of light. Third, for each metal there is a characteristic minimum frequency nu naught, also known as threshold frequency. What is known as threshold frequency? Nu naught. Okay, for each metal there is a characteristic minimum frequency nu naught, also known as threshold frequency, below which photoelectric effect is not observed. At a frequency nu greater than nu naught, the ejected electrons come out with certain kinetic energy. The kinetic energies of these electrons increase with the increase of frequency of the light's use. All the above results could not be explained on the basis of laws of classical physics. According to the latter, the energy content of the beam of light depends upon the brightness of the light. In other words, number of electrons ejected and the kinetic energy associated with them should depend on the brightness of light. It has been observed that though the number of electrons ejected does not depend on the brightness of light, the kinetic energy of the ejected electrons does not. For example, red light nu is equal to 4.3 to 4.6 10 to the power 14 hertz of any brightness intensity may shine on a piece of potassium metal for hours, but no photoelectrons were ejected. But as soon as a very weak yellow light, nu is equal to 5.1 to 5.2 into 10 to the power 14 hertz, shines on the potassium metal, the photoelectric effect is observed. The threshold frequency nu naught for potassium metal is 5.0 into 10 to the power 14 hertz. Okay, Einstein 1905 was able to explain the photoelectric effect using Planck's quantum theory of electromagnetic radiation as a starting point. Let's study about Albert Einstein. Albert Einstein, a German-born American physicist, is regarded by many as one of the two great physicists of the world known. The other is Isaac Newton. His three research papers on a special relativity, Brownian motion, and the photoelectric effect, which he published in 1905 while he was employed as a technical assistant in a Swiss patent office in Bern, have profoundly influenced the development of physics. He received the Nobel Prize in Physics in 1921 for his explanation of photoelectric effect. Shining a beam of light on a metal surface can therefore be viewed as a shooting a beam of particles, the photons. When a photon of sufficient energy strikes an electron in the atom of metal, it transfers its energy instantaneously to the electron during the collision, and the electron is ejected without any time lag or delay. Greater the energy possessed by the photon, greater will be transfer the energy to the electron, and greater the kinetic energy of the electron ejected. In other words, kinetic energy of the ejected electron is proportional to the frequency of the electromagnetic radiation. Since the striking photon has energy equal to h nu, and the minimum energy required to eject the electron is h nu naught, also known as work function W naught, table 2.2. Okay, the work function of different metals is shown here. Okay, then the difference in energy h nu minus h nu naught is transferred as the kinetic energy of the photoelectron. Following the conservation of energy principle, the kinetic energy of the ejected electron is given by the equation 2.7. H nu is equal to h nu naught plus half me v square. H nu is equal to h nu naught plus half me v square. This is equation 2.7, and uh, this is derived from the conservation of energy principle. Okay, let us have a look on the table 2.2, values of work function for few metals. Okay, value of work function for few metals such as lithium, sodium, potassium, magnesium, copper and silver, and the work function are respectively 2.40, 2.3, 2.25, 3.7, 4.8, 4.3. I don't know why it is given. Okay, later हो सकता है पता चल जाए. So we were on the 2.7 equation. H nu is equal to h nu naught plus half MeV square, where Me is the mass of electron and V nu is the velocity associated. Is this nu or this is V? What is it? Of course this is nu. Yes, this is nu, not V. Okay, let it be anything, where Me, okay, Me is the mass of the electron, and here should be means capital V. Capital V is of course the velocity associated with the ejected electron. I don't know why it is given here small v. Okay, so in the figure capital V is denoting velocity. I know this pakka. Lastly, a more intense beam of light consists of larger number of photons. Consequently, that number of electrons ejected is also larger as compared to that in an experiment in which a beam of weaker intensity of light is employed. Dual behavior of electromagnetic radiation. The particle nature of light posed a dilemma for scientists. On the other, on the one hand, it could explain the blackbody radiation and the photoelectric effect satisfactorily, but on the other hand, it was not consistent with the known wave behavior of light, which could account for the phenomena of interference and diffraction. The only way to resolve the dilemma was to accept the idea of light possesses both particle and wave like properties, that is, light has dual behavior. Depending on the experiment, we find that light behaves either as a wave or as a stream of particles. Whenever radiation interacts with matter, it displays particle-like properties in contrast to the wave-like properties in bracket interference and diffraction, which it exhibits when it propagates. This concept was totally alien to the way of scientists, though about matter and radiation it took them a long time to become convinced of its validity. It turns out, as you shall see later, that some microscopic particles like electrons also exhibit this wave particle duality. Okay, okay. We are on page number 43 and problem 2.6. Calculate the energy of 1 mole of photons of radiation whose frequency is 5.10 to the power 14 hertz. Solution. Energy E of one photon is given by expression E is equal to h nu. H is equal to 6.626 into 10 power minus 34 joule second. In other words, H is equal to chakka to chakka into 10 to the power minus 34 joule second. Nu is equal to 5 into 10 to the power 14 per second given. Is equal to 6.626 into 10 to the power minus 34 joule second, and for 5 into 10 to the power 14 joule per second is equal to 3.313 into 10 to the power minus 19 joule. Energy of 1 mole of photons is equal to 3.313 into 10 to the power minus 19 joule into 10 to into 6.022 into 10 to the power 23 mole, this is per mole, is equal to 199.51 kilojoule per mole. Problem 2.7. A 100-watt bulb emits monochromatic light of wavelength 400 nanometer. Calculate the number of photons emitted per second by the bulb. Power of the bulb is 100 watts, 100 joule per second. Energy of one photon is equal to h nu is equal to hc by lambda 6.626 into 10 to the power minus 34 joules second into 3 into 10 to the power 8 meter per second by 400 into 10 to the power minus 9 meter is equal to 4.969 into 10 to the power minus 9 joule. Number of electrons emitted will be 100 joule per second by 4.969 into 10 to the power minus 19 joule. That gives finally 2.012 into 10 to the power 20 per second. Problem 2.8. What is it? When electromagnetic radiation of wavelength 300 nanometer falls on the surface of sodium, electrons are emitted with a kinetic energy of 1.6 into 10 to the power 5 joule per mole. What is the minimum energy needed to remove an electron from the sodium? What is the maximum wavelength that will cause a photoelectron to be emitted? Okay, we have been asked two questions. What is the minimum energy needed to remove an electron from the sodium first, and what is the maximum wavelength that will cause a photoelectron to be minimum maximum electron energy so that the electron could be emitted. This is simply asked, यही पूछा गया है ना. चलिए solution. The energy E of 300 nanometer photon is given by Hn is equal to Hc by lambda. What is this Hn? Where this n came from here? Okay, mention not might it be some, might it be, खैर जो भी हो सकता है मिसप्रिंट हुआ तो बाद में समझ में आ जाएगा, आगे समझ में आ जाएगा. ओके, प्रोसीड करिए. द एनर्जी ई ऑफ 300 नैनोमीटर फोटोन इज गिवन बाई एच एन इज इक्वल टू एच सी बाई लैम्डा. ऊपर देखता हूँ कहीं कुछ मिल जाए. एच न्यू इज इक्वल टू बाई लैम्डा. ई इज इक्वल टू एच न्यू होता है, और हमें क्या पता था, और भी कुछ पता था हमें. डिड वी न्यू समथिंग आल्सो? ओके, आई डोंट नो. Yes, we were here. The energy E of 300 nanometer photon is given by Hn is equal to Hc by lambda is equal to 6.626 into 10 to the power minus 34 joules, 3.0 into 10 to the power 8 meter per second by 300 into 10 to the power minus 9 meter is equal to 6.626 into 10 to the power minus 19 joule. The energy of 1 mole of photons is equal to 6.626 into 10 to the power minus 19 joule into 6.022 into 10 to the power 23 mole per mole is equal to 3.99 into 10 to the power 5 joule per mole. The minimum energy needed to remove 1 mole of electrons from sodium is equal to 3.99 minus 3.99 minus 1.68 in bracket into 10 to the power 5 joule per mole finally gives 2.31 into 10 to the power 5 joule per mole. The minimum energy for one electron is equal to 2.31 into 10 to the power 5 joule per mole by 6.022 into 10 to the power 23 electrons per mole is equal to 3.84 into 10 to the power minus 19 joule. This corresponds to the wavelength. So lambda is equal to Hc by E is equal to 6.626 into minus 34 joule second into 10 to the power into 3.0 into 10 to the power 8 meter per second by 3.84 into 10 to the power minus 19 joule. Finally it is 517 nanometer. This corresponds to green light. Problem 2.9. The threshold frequency nu naught for a metal is 7.0 into 10 to the power 14 per second. Calculate the kinetic energy of an electron emitted when radiation of frequency nu is equal to 1.0 into 10 to the power 15 per second hits the metal. Solution. According to the Einstein's equation, kinetic energy is equal to half MeV square is equal to H into V minus V naught is equal to 6.626 into 10 to the power minus 34 joules second into 1.0 into 10 to the power 15 per second minus 7.0 into 10 to the power 14 per second. 6.626 into 10 to the power minus 34 joules second in bracket 10.0 into 10 to the power 14 per second minus 7.0 minus 7.0 into 10 to the power 14 per second is equal to 6.626 into 10 to the power minus 34 joules second into 3.0 into 10 to the power 14 per second is equal to 1.988 into 10 to the power minus 19 joule. 44 नंबर पेज पे और on the 44 number page 2.3.3 evidence for the quantized electronic energy levels atomic spectra. The speed of light depends upon the nature of the medium through which it passes. As the result, the beam of light is deviated or refracted from its original path. It passes from one medium to another. It is observed that when a ray of light passes through a prism, the wave with shorter wavelength bends more than the one with a longer wavelength. Since ordinary white light consists of waves with all the wavelengths in the visible range, a light of white light is spread out into a series of colored bands called spectrum. The light of red color, which has the longest wavelength, is deviated the least, while the violet light, which has the shortest wavelength, is deviated the most. The spectrum of the white light that we can see ranges from violet at 7.50 into 10 to the power 14 hertz to red at 4 into 10 to the power 14 hertz. Such a spectrum is called continuous spectrum. Continuous because violet merges into blue, blue into green, so on. A similar spectrum is produced when a rainbow forms in the sky. Remember that visible light is just a small portion of the electromagnetic radiation that was shown in figure 2.7. When electromagnetic radiation interacts with matter, atoms and molecules may absorb energy and reach to the higher energy state. With higher energy, these are in an unstable state. For returning to their normal in bracket more stable lower energy states, okay, the atoms and the molecules emit radiation in various regions of the electromagnetic spectrum. Emission and absorption of spectra. The spectrum of the emission and absorption spectra. The spectrum of radiation emitted by a substance that has absorbed energy is called an emission spectrum. Atoms, molecules, and ions that have absorbed radiation are said to be excited to produce an emission spectrum. Energy is supplied to a sample by heating it or irradiating it, and the wavelength or frequency of the radiation emitted as the sample gives up the absorbed energy is recorded. An absorption spectrum is like the photographic negative. An absorption spectrum is like the photographic negative of an emission spectrum. The a continuous continuum of radiation. I don't know what is this continuum. A continuum of radiation is passed through a sample which absorbs radiation of certain wavelengths. The missing wavelength, which corresponds to the radiation absorbed by the matter, leave dark spark spaces in the bright continuous spectrum. The study of emission or absorption spectra is referred to as spectroscopy. The spectrum of the visible light, as discussed above, was continuous as all wavelength red to violet to the visible light are represented in the spectra. The emission spectra of atoms in the gas phase, on the other hand, do not show a continuous spread of wavelength from red to violet. Rather, they emit light only at specific wavelengths with dark spaces between them. Such spectra are called line spectra or atomic spectra because the emitted radiation is identified by the appearance of bright lines in the Spectra, figure 2.10, page 45. Line spectra. Line emission spectra are of great interest in the study of electronic structure. Each element has a unique line emission spectrum. The characteristic lines in the atomic spectra can be used in different analyses to identify unknown atoms in same way as the fingerprints are used to identify people. The exact matching the lines of the emission spectrum of the atoms of unknown element which the of a known element of a known element with the lines from an unknown sample quickly establishes the identity of the latter. German chemist Robert Bunsen (1811 to 1899) was one of the first investigators to use line spectra to identify elements like rubidium (Rb, cesium, Cs, thallium, Tl, indium, iron, gallium, Ga, scandium, Sc were discovered when their minerals were analyzed by the spectroscopic methods. Okay, this becomes a very good question. Okay, ध्यान रखिएगा, अच्छा क्वेश्चन बनता है कैसे इन सब की खोज हुई थी स्पेक्ट्रोस्कोपिक मेथड के द्वारा एनालाइज जब किया गया तभी. ठीक है. द एलिमेंट्स helium He was discovered in the sun by spectroscopic method. Line spectrum of hydrogen. When an electric discharge is passed through gaseous hydrogen, the H2 molecules dissociate and energetically excited hydrogen atoms produced emit electromagnetic radiation of discrete frequencies. Light spectrum of hydrogen. When an electric discharge is passed through gaseous hydrogen, the H2 molecules dissociate and energetically excited hydrogen atoms produced emit electromagnetic radiation of discrete frequencies. The hydrogen spectrum consists of several series of lines named after their discoverers. Balmer showed in 1885 on the basis of experimental observations that if spectral lines are expressed in terms of wave number, that is nu bar, then the visible line of the hydrogen spectrum obey the following formula. Nu bar is equal to 109677 into 1 by 2 square minus 1 by n square per centimeter. This is equation 2.8, where n is an integer equal to or greater than 3, in bracket, that is n is equal to 3, 4, 5. The series of lines described by this formula are called the Balmer series. The Balmer series of lines are the only lines in the hydrogen spectrum which appears in the visible region of the electromagnetic spectrum. The Swedish spectroscopist Johannes Rydberg noted that all series of lines in the hydrogen spectrum could be described by the following expression. Nu bar is equal to 109677 into 1 by n1 square minus 1 by n2 square per centimeter, where n1 is equal to 1, 2, n2 is equal to n1 plus 1 and 1 plus 2 dash dash dash. The value 109677 per centimeter is called the Rydberg constant for hydrogen. The first 5 series of lines that correspond to n1 is equal to 1, 2, 3, 4, 5 are known as Lyman-Balmer, Paschen, bracket and Pfund series respectively. Table 2.3 shows these series of transitions in the hydrogen spectrum. Figure 2.11, page 46 shows the Lyman-Balmer and Paschen series of the transitions for hydrogen atom. Of all the elements, hydrogen atom has the simplest line spectrum. Line spectrum becomes rationalize many points in the atomic structure. Spectra. Bohr's model for hydrogen atom is based on the following postulates. Before we study this following postulate, let us get back to the last chapter where we have okay, we have left this figure 2.10a, atomic emission. The light emitted by a sample of excited hydrogen atoms for any other element can be passed through a prism and separated into certain discrete wavelengths. Thus, an emission spectrum, which is a photographic recording of the separated wavelengths, is called as line spectrum. Any sample of reasonable size contains an enormous number of atoms, although a single atom can be used in only excited state at a time. The collection of atoms contains all possible excited states. The light emitted as these atoms fall to lower energy states is responsible for the spectrum. B. Atomic absorption. When white light is passed through unexcited atomic hydrogen and then through a slit and prism, the transmitted light is lacking in intensity at the same in the same once again atomic absorption. When white light is passed through unexcited atomic hydrogen and then through a slit and prism, the transmitted light is lacking in intensity at the same wavelengths as are emitted in A. The recorded absorption spectrum is also a line spectrum and the photographic negative of the emission spectrum. क्या दिखता है ये ए और बी में एक्साइटेड सैंपल एक डिस्क के अंदर से लाइट आ रही है, फिर एक बैरियर से पास कराया जा रहा है, प्रिज्म से होकर के गुजरने पर ये वाइट लाइट जो है 7 कलर्स में डिफ्लेक्ट हो जा रहा है, जो एक फिल्म डिटेक्टर पे दिखाई भी दे रहा है। इंक्रीजिंग वेवलेंथ, और वेवलेंथ का बढ़ना हम देख सकते हैं एमिशन स्पेक्ट्रम। और बी में ये क्या दिखाई दे रहा है, वाइट लाइट सोर्स। अच्छा, यहाँ से उजले लाइट को एब्जॉर्प्शन सैंपल यहाँ से किया गया, तो ये भी 7 जगह पे फिल्म डिटेक्टर हुआ, लेकिन इंक्रीजिंग एब्जॉर्प्शन स्पेक्ट्रम। इन दोनों में क्या अंतर है? एटॉमिक एमिशन और एटॉमिक एब्जॉर्प्शन। इंक्रीजिंग वेवलेंथ, दोनों में वेवलेंथ इंक्रीज हो रहा है, लेकिन एक एमिशन स्पेक्ट्रम है, एक एब्जॉर्प्शन स्पेक्ट्रम है। पता नहीं। ओके, टेबल 2.3 भी बाकी रह गया था अपना। टेबल 2.3 स्पेक्ट्रल लाइंस ऑफ फॉर एटॉमिक हाइड्रोजन। तो सीरीज में लाइमन बामर पार्शियल ब्रैकेट पी फंड N1 and N2 for N1 1 2 3 4 5 respectively, and N2 2 3 3 4 4 5 5 6 6 7 and dash 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 for each of the spectral region will be for Lyman it is ultraviolet, for Balmer visible, partial infrared bracket infrared P fund infrared. Okay, and in figure 2.11 transitions of the electron in the hydrogen atom, the diagram shows the Lyman-Balmer partial series of transitions. Okay, the figure shows the Lyman-Balmer partial series of transitions. Okay, so we were here from last, and of all the elements, hydrogen atom has the simplest line spectrum. Line spectrum becomes rationalize many points in the atomic structure and spectra. Bohr model for hydrogen atom is based on the following postulates. First, the electron in the hydrogen atom can move around the nucleus in a circular path of fixed radiation energy. These paths are called orbits. Stationary states are allowed energy states. These orbits are arranged concentrically around the nucleus. Second, the energy of an electron in the orbit does not change with time. However, the electron will move from lower stationary state to a higher stationary state when required amount of energy is absorbed by the electron, or energy is emitted when electron moves from higher stationary state to lower stationary state. In figure equation 2.16, the energy change does not take place in a continuous manner. Angular momentum, just as linear momentum is the product of mass and linear velocity v, angular momentum is the product of moment of inertia I and angular momentum omega. For an electron of mass me moving in a circular path of radius r around the nucleus, angular momentum is equal to I moment of inertia into omega, that is angular velocity. So since I is equal to MER square and omega is equal to V by R, where V is the linear velocity, so angular momentum is equal to MER square into V by R is equal to MEVR. Third point, the frequency of radiation absorbed or emitted when transition occurred. Yes. Third, the frequency of the radiation observed hey sorry we have just we have distracted from the our actual sequence of reading. Here, after the last line of this page, on the right side, last para, of all the elements, hydrogen atom has the simplest line spectrum. Line spectrum becomes, and then we'll start from here, becomes more and more complex for heavier atom. There are, however, certain features which are common to all line spectra. That is, first, line spectrum of element is unique, and second, there is a irregularity in the line spectrum of each element. The questions which arise are, what are the reasons for the similarities? Is it something to do with the electronic configuration of atoms? These are questions needed to be answered. We shall find later that the answers to these questions provide the key in understanding electronic structure of these elements. 2.4, Bohr model for hydrogen atom. Niels Bohr in 1930 was the first to explain quantitatively the general features of the structure of hydrogen atom in spectrum. He used Planck's concept of quantization of energy. Though the theory is not modern quantum mechanics, it can still be used to rationalize many points in the atomic structure and spectra. अपना बैठ रहा है ठीक है. Now this is good sequence. Bohr model for hydrogen atom is based on the following postulates. Bohr's model for hydrogen atoms is based on the following postulates. First, electron is the electron in the hydrogen atom can move around the nucleus in a circular path of fixed radius and energy. These paths are called orbit. Stationary states or allowed energy states. These orbits are arranged concentrically around the nucleus. Second, concentrically मतलब एक दूसरे के चारों तरफ बिल्कुल गोलाकार स्थिति में. Second, the energy of an electron in orbit does not change with the time. However, the electron will move from a lower energy state to a higher energy state when required amount of energy is absorbed by the electron, or energy is emitted when electron moves from high stationary state to lower stationary state. Question 2.16, the energy change does not take place in continuous manner. Third, the frequency of radiation absorbed or emitted when transition occurs between two stationary states that differ in energy by delta E is given by V is equal to delta E by H is equal to E2 minus E1 by H. This is 2.10, equation 2.10. What is V is equal to delta E by H is equal to, is this V or is this nu? No, this is nu, not V. Okay, so we get here a new formula for nu. Nu is equal to delta E by H is equal to E2 minus E1 by H. This is equation 2.10, where E1 and E2 are the energies of the lower and higher allowed energy states. The expression is commonly known as Bohr's frequency rule. This expression is commonly known as Bohr's frequency rule. So कोई पूछेगा Bohr's frequency rule क्या था, क्या बताओगे भैया? बताओगे फ्रीक्वेंसी रूल था न्यू इज इक्वल टू डेल्टा ई बाई एच. बस बात खत्म. बोर का फ्रीक्वेंसी रूल था ये, बात खत्म. और यहाँ से चूँकि फ्रीक्वेंसी रूल था ये, तो फ्रीक्वेंसी का साइन होता है न्यू. पता चल गया ये न्यू है. ओके. फोर्थ, द एंगुलर momentum of the electron is quantized in a given stationary state. It can be expressed as in equation 2.11. MEVR is equal to NH by 2 pi, where n is equal to 1, 2, 3 dash dash dash. This is equation 2.11. Okay, page number 47, where Ma is the mass of electron, Ma is the mass of electron, where in equation 2.11, where Ma is the mass of electron, nu is the, here this is not nu, this is V. Okay, V is the, ये मिस्टेक किया हुआ है, प्रिंटिंग मिस्टेक है, यहाँ पे न्यू लिख दिया है, V होना चाहिए ना. ठीक है, न्यू का तो उसमें जिक्र ही नहीं है 2.11 में. Nu is the velocity and r is the radius of the orbit in which electron is moving. Thus, an electron can move only in those orbits for which its angular momentum is a integral multiple of h by 2 pi. That means angular momentum is quantized. Radiation is emitted or observed only when transition of electron takes place from one quantized value of angular momentum to another. Therefore, Maxwell's electromagnetic theory does not apply here. That is why only certain fixed orbits are allowed. The details regarding the derivation of energies of the stationary states used by Bohr in higher classes. However, according to Bohr's theory of hydrogen atom, the stationary states for electron are numbered. N is equal to 1, 2, 3 dash dash dash. These integral numbers section 2.6.2 are known as principal quantum numbers. B. The radii of the stationary states are expressed as Rn is equal to n square a naught in bracket 2.12. This is equation 2.12 to 2.12. Rn is equal to n square a naught, where a naught is equal to 52.9 pm. Thus, the radius of the first stationary state called the Bohr orbit is 52.9 pm. Normally, the electron in the hydrogen atom is found in this orbit, that is n equal to 1. As n increases, the value of r will decrease. In other, as n increases, the value of r will increase. In other words, the electron will be present away from the nucleus. See, the most important property associated with the electron is the energy of its stationary state. It is given by the expression En is equal to minus RH into 1 by n square, where n is equal to 1, 2, 3 dash dash dash. This is 2.13 equation, where RH is the Rydberg constant. Here is the new constant. इससे पहले प्लैंक्स कांस्टेंट पढ़ा था, छक्का वाला, याद है ना? छक्का 2 छक्का इंटू 10⁻34. जूल होता है, ठीक है, मत भूलिएगा। और यहाँ पे रिडबर्ग कांस्टेंट, तो इसका ये फॉर्मूला नहीं है, बस आपको रखना होगा माइनस रिडबर्ग कांस्टेंट आर एच कहा जाता है फिर आर एच, एंड इट्स वैल्यू इज 2.18 इंटू 10⁻−18 जूल, 2.18 इंटू 10⁻−18 जूल। The energy of the lowest state, also called as the ground state, is E1 is equal to minus 2.18 10⁻−18. 1 by 1 square is equal to minus 2.18 10⁻−18 joule. The energy of the stationary state for n is equal to 2 will be E2 is equal to minus 2.18 10⁻−18 joule into 1.2 square is equal to minus 0.545 into 10⁻18 joule. Okay, now let us know something about Niels Bohr. He lived from 1885 to 1962, मतलब 15 साल बाद तक जीते रहे हैं। नेहरू जी के 2 साल पहले तक जिंदा रहे, आज़ादी के 15 साल बाद तक जिंदा रहे थे हमारे Niels Bohr, a Danish physicist. Niels Bohr, a Danish physicist, received his PhD from the University of Copenhagen in 1911. He then spent a year with J.J. Thomson and Ernest Rutherford in England. In 1930, he returned to Copenhagen, where he remained for the rest of his life. In 1920, he was named director of the Director of Institute of Theoretical Physics. After First World War, Bohr worked energetically for peaceful uses of atomic energy. He received the first Atoms for Peace awards. He received the first Atoms for Peace award in 1957. Bohr was awarded the Nobel Prize in Physics in 1922. Figure 2.11 कहाँ है? Figure 2.11 भाई कहाँ है? Figure 2.11 हाँ यहाँ रहा। तो Figure 2.11 हाँ Figure 2.11 depicts the energies of different stationary orbits of energy levels of hydrogen atom. This representation is called an energy level diagram. चलिए देखिए लेते हैं, जिनको स्क्रीनशॉट लेना है समझने के लिए समझ लीजिए, ठीक है, ये रहा। ओके, this message only. Okay, so figure 2.11 depicts the energies of different stationary in states of or energy levels of hydrogen atom. This representation is called an energy level diagram. समझ गए? Energy level diagram कहते हैं उसको. When the electron is free from the influence of nucleus, the energy is taken as zero. The electron is in this situation is situated with the energy with the stationary state of principal quantum number is equal to n is equal to infinity, is called as ionized hydrogen atom. When the electron is attracted by the nucleus and is present in orbit n, the energy is emitted. What does the negative electronic energy En for hydrogen atom mean? ये what does the negative electronic energy, नेगेटिव इलेक्ट्रॉनिक एनर्जी क्या होता है एटम का, हाइड्रोजन एटम का क्या होता है इसका मतलब? The energy of the electron in a hydrogen atom has a negative sign for all possible orbits. Equation 2.13 से साबित होता है, जस्ट लेफ्ट में ही है, देखिए यहाँ पे जस्ट लेफ्ट में ही है. What does the negative sign convey? This negative sign means that the energy of the electron in the atom is lower than the energy of the free electron at rest. A free electron at rest is an electron that is infinitely far away from the nucleus and is assigned the energy value of 0. Mathematically, this corresponds to the setting n equal to infinity in the equation 2.13, so that E infinity is equal to 0. As the electron gets closer to the nucleus, as n decreases, En becomes larger in absolute value and more negative. The most negative energy value is given by n is equal to 1, which corresponds to the most stable orbit. We call this ground. We call this the ground state. Page number 48. And its energy is lowered. तो यहाँ से पिछले से कंटिन्यू करते हैं. यहाँ पे थे हम लोग just above this greenish boundary. When the electron is attracted by the nucleus, जब इलेक्ट्रॉन न्यूक्लियस के द्वारा अट्रैक्ट किया जाता है एंड इज प्रेजेंट इन ऑर्बिट n, और किसी n ऑर्बिट में है कोई n, तो द एनर्जी इज एमिटेड. तो जो एनर्जी एमिट होता है, निकलते रहता है मूव करते टाइम में, एंड इट्स एनर्जी इज लोअर. अच्छा, निकलते रहता है एंड इट्स एनर्जी इज लोअर, और ये द एनर्जी इज एमिटेड एंड इट्स एनर्जी इज लोअर. तो एमिट होगा तो कम होगा ही. दैट इज द रीजन फॉर द प्रेजेंस ऑफ नेगेटिव साइन ऑफ इलेक्ट्रॉन. इक्वेशन 2.13. अच्छा, अभी तक उसी पे मुद्दा चल रहा है. एंड डिपिक्ट stability relative to the reference state of zero energy and n is equal to infinity. D. Bohr's theory can also be applied to the ions containing only one electron, similar to that present in a hydrogen atom. For example, He plus, Li2 plus, P3 plus, and so on. The energies of the stationary states associated with these kinds of ions, also known as hydrogen-like species, are given by the expression En is equal to minus 2.18 into 10 to the power minus 18 in brackets z square by n square joule 2.14, and radii by the expression Rn is equal to 52.9 in bracket n square by z pm. This is equation 2.15. So equation 2.14 is En is equal to minus 2.18 into 10 to the power minus 18 in bracket z square by n square joule, and equation 2.15 is Rn is equal to 52.9 by 52.9 n square by z, capital Z, pm, picometer, where z is the atomic number and has values 2, 3 for the helium and lithium atoms respectively. From the above equations, it is evident that the value of energy becomes more negative and that of radius becomes smaller with the increase of z. सही बात है, z के बढ़ने से जो वैल्यू ऑफ एनर्जी है वो घट जाता है, नेगेटिव. From the above, it is evident that the value of energy becomes more negative and that of radius becomes smaller with increase of z. This means that the electron will be tightly bound to the nucleus, और जिससे पता चलता है कि ज़्यादा से ज़्यादा जोर से बंधा रहेगा न्यूक्लियस के साथ. ज़्यादा नेगेटिव चार्ज होगा तो अट्रैक्शन ज़्यादा बढ़ेगा, तो ज़्यादा बनते रहेगा ना भाई. E. It is also possible to calculate the velocities of electrons moving in these orbits, although the precise equation is not given here. Qualitatively, the magnitude of the velocity of electron increases with the increase of positive charge on the nucleus and decreases with the increase of principal quantum number. 2.4.1 Explanation of line spectrum of hydrogen. Line spectrum observed in case of hydrogen atom as mentioned in section 2.3.3. Line spectrum observed in case of hydrogen atom as mentioned in section 2.3.3 can be explained quantitatively using Bohr's model. According to assumption 2, radiation energy is absorbed in the electron moves from according to assumption 2, radiation, that is energy, is absorbed if the electron moves from the orbit of smaller principal quantum number to the orbit of higher principal quantum number, where the radiation energy is emitted if the electron moves from higher energy to lower energy, the energy gap between the two orbits is given by the equation 2.16, that is delta is equal to E T E final minus E initial. Combining the equations 2.13 and 2.16, we find this delta E is equal to under bracket minus RH by NF square minus under bracket minus RH by Ni square, where Ni and Ni stand for the initial orbit and final orbits. Okay, delta E is equal to RH into in bracket 1 by Ni square minus 1 by Nf square is equal to 2.18 into 10 to the power minus 18 joule in bracket 1 by Ni square minus 1 by Nf square. This is 2.17 equation. The frequency nu associated with the absorption and emission of the photon can be evaluated by using equation 2.18. And what is the equation 2.18, friends? Nu is equal to delta E by H is equal to RH by H into 1 by Ni square minus 1 by Nf square, and that is equal to 2.18 into 10 to the power minus 18 joule by 6.626 into 10 to the power minus 34 joule second into 1 by Ni square minus 1 by Nf square. This is our 2.18 equation is equal to 3.29 root 10 to the power 15 into 1 in bracket 1 by Ni square minus 1 by Nf square hertz. This is equation 2.19. And in terms of wavelength, wave numbers in bracket nu bar is equal to nu by C is equal to Rc by Hc in bracket 1 by Ni square minus 1 by Nf square. This is equation 2.20 is equal to 3.29 into 10 to the power 15 per second by 3 into 10 to the power 8 meter per second into in bracket 1 by Ni square minus 1 by Nf square is equal to 1.09677 into 10 to the power 7 in bracket into in bracket 1 by Ni square minus 1 by Nf square per meter. This is equation 2.21. धड़ाधड़ के बाद एक equation. Okay, धड़ाधड़ one equations. In case of absorption spectrum, where Nf is greater than Ni, and in case of absorption spectrum, where Nf is greater than Ni, that means that okay, final energy orbits. This is final orbits. So in case of final orbit is greater than initial orbit, and the terms in the parenthesis is positive. And what do you mean by parenthesis? Do you know? Don't you know parenthesis? Oh, parenthesis, that means just like on the lower right side of anything. Okay, and the term in the parenthesis is positive and energy, and the term in the parenthesis is positive and energy is absorbed. Sorry, I don't हमको याद नहीं आ रहा है parenthesis का मतलब. सॉरी, गलत जानकारी तो नहीं दे सकते हैं यार, फ्यूचर बर्बाद होने का टेंशन रहता है, किसी ने विश्वास कर लिया गलती से तो ठीक है भाई. चलो parenthesis देख लेना. इन केस ऑफ, थोड़ी देर में याद आ जाएगा, पता नहीं कभी याद आएगा. In case of absorption spectrum, Nf is greater than Ni, and the term in the parenthesis is positive and the energy is absorbed. On the other hand, in case of emission spectrum, Ni is greater than Nf, that is delta E is negative and energy is released. The expression 2.17 is similar to that used by Rydberg in bracket 2.19, derived empirically using the experimental data available at that time. Further, each special spectral line, whether in absorption or emission spectrum, can be associated to the particular transition in hydrogen atom. In case of large number of hydrogen atom, different possible transition can be observed, and thus leading to large number of spectral lines. The brightness or intensity of spectral lines depends upon the number of photons of same wavelength or frequency absorbed or emitted. प्रॉब्लम 2.110 फ्रेंड्स सी योर सेल्फ अपने आप से 2.10 प्रॉब्लम नंबर करिएगा, करने की चीज़ है, ठीक है। क्वेश्चन है कि व्हाट आर द फ्रीक्वेंसीज एंड वेवलेंथ ऑफ प्रोटॉन एमिटेड ड्यूरिंग अ ट्रांजिशन फ्रॉम n इज इक्वल टू 5 स्टेट टू n इज इक्वल टू 2 स्टेट इन द हाइड्रोजन एटम, ठीक है। और प्रॉब्लम 2.11 says that calculate the energy associated with the first orbit of He plus के फर्स्ट ऑर्बिट का एनर्जी पूछ रहा है। व्हाट इज द रेडियस ऑफ दिस ऑर्बिट, और इस ऑर्बिट का रेडियस भी पूछ रहा है। चलिए अब आता है हमारा नेक्स्ट टॉपिक 49 नंबर पेज का, फुट नंबर पेज का 2.4.2 limitations of Bohr model. Bohr's model of hydrogen atom was no doubt an improvement over Rutherford's nuclear model, as it could account for the stability and light spectra of hydrogen atom. तो बेशक बोर का मॉडल रदरफोर्ड के मॉडल से अच्छा था, और ये पता नहीं क्यों ये कंपेयर कर रहा है, क्योंकि जितना टफ पढ़ाई बोर का मॉडल में है रदरफोर्ड में तो कुछ भी नहीं है, तो ये कंपैरिजन ही बेहुदा है। और ये कहना कि जस्ट वाज एन इम्पॉर्टेंट नो डाउट, ये तो खैर सोचने की वाली बात नहीं है, वो तो श्योर पता ही चलता है। चलिए तो देखते हैं। बोर मॉडल ऑफ हाइड्रोजन एटम वाज नो डाउट एन इम्प्रूवमेंट ओवर रदरफोर्ड्स न्यूक्लियर मॉडल, and it could account for the stability and line spectra of hydrogen atom and hydrogen like ions, for example He plus, Li2 plus, Be3 plus, and so on. However, Bohr's model was too simple to account for the following points. It fails to account for the finer details, doublet, that is too closely spaced lines of the hydrogen atom spectrum observed by using sophisticated spectroscopic techniques. This model is also unable to explain the spectrum of atoms other than the hydrogen. For example, helium atom, which possesses only 2 electrons. Further, Bohr's theory was also unable to explain the splitting was unable to Further, Bohr's theory was also unable to explain the splitting of spectral lines in the presence of magnetic field, Zeeman effect, that is known as, or an electric field, that is Sark effect. Second, it could not explain the stability of atoms to form molecules by chemical bonds. In other words, taking into account the points mentioned above, one needs a better theory which can explain the salient features of the structure of complex atoms. 2.5 towards quantum mechanical model of the atom. In the view of shortcoming of the Bohr's model, attempts were made to develop a more suitable and general model for atom. Two important developments which contributed significantly in the formulation of such a model were: first, dual behavior of matter; second, Heisenberg uncertainty principle. So 2.5.1 dual behavior of matter. A French physicist de Broglie in 1924 proposed that matter like radiation should also exhibit dual behavior, that is both particle and wave like properties. This means that if just as the photon has momentum as well as wavelength, electron should also have momentum as well as wavelength. De Broglie from his analogy gave the following relation between wavelength lambda and momentum p of the following of material particle. तो लुइस डी ब्रोगली के बारे में कुछ पढ़ लेते हैं. लेट्स स्टडी समथिंग अबाउट लुइस डी ब्रोगली, his about his, and then we will proceed our previous study. Louis de Broglie, a French physicist, studied history as an undergraduate in the early 1910s. अच्छा बात है, हिस्ट्री पढ़ के विद्वान भाई साइंटिस्ट बन गया. खैर देखिए, ये हम सब के लिए मोटिवेशन है. इट्स अ ग्रेट मोटिवेशन फॉर ऑल वी स्टूडेंट्स. चलिए तो अंडर ग्रेजुएशन जो ये हिस्ट्री में किए हैं, interest turned into science as a result of assignment to radio communications in World War I. He received his doctor as in Dr. SC, Doctor Science from the University of Paris in 1924. He was professor of theoretical physics at the University of Paris from 1932 until his retirement in 1962. He was awarded the Nobel Prize in Physics in 1929. तो हम लोग का प्रीवियस स्टडी कहाँ चल रहा था? But before it, we were here that 2.5.1 Dual behavior of matter. The French physicist de Broglie in 1924 proposed that matter-like radiation should also exhibit dual behavior, that is both particle and wave-like properties. This means that just as photon has momentum as well as wavelength, electron should also have momentum as well as wavelength. De Broglie, from his analogy, gave the following relationship between wavelength lambda and momentum p of the following of the material particle, and the relation was lambda is equal to h by mv is equal to h by p. This is 2.22 equation number, where m is the mass of particle, v is velocity, p is momentum. De Broglie's prediction was confirmed experimentally when it was found that an electron beam undergoes diffraction, a phenomenon characteristic of waves. This fact has been put to use in making an electron microscope, which is based on the wave-like behavior of electrons, just as an ordinary microscope utilizes the wave nature of light. An electron microscope is a powerful tool in modern scientific research because it achieves a magnification of about 15 million times. It needs to be noticed that according to de Broglie, every object in the motion has a wave character. The wavelengths associated with ordinary objects are so short because of their large masses that their wave properties cannot be detected. The wavelengths associated with the electrons and other subatomic particles with very small mass can, however, be detected experimentally. Results obtained from the following problems prove these points qualitatively. तो ये कह रहा है, नीचे लिखे गए the following problems, the results obtained prove the points quantitatively. ठीक है, तो चलिए इन प्रॉब्लम्स को हम लोग देखते हैं. प्रॉब्लम 2.2, what will be the wavelength of a ball of mass 0.1 kg moving with a वेलोसिटी ऑफ 10 मीटर पर सेकेंड. 10 मीटर पर सेकेंड की रफ्तार से 100 ग्राम का बॉल है, 0.1 kg 100 ग्राम हुआ. 100 ग्राम का बॉल 10 मीटर पर सेकेंड की रफ्तार से चल रहा है, तो इसका वेवलेंथ कुछ होगा क्या? हाँ, डी ब्रॉगली जी के अनुसार से हर मूविंग पार्टिकल का एक वेवलेंथ होना चाहिए. जितना स्मॉल पार्टिकल होगा उतना ही, और हल्का पार्टिकल होगा, आसान होगा इसका वेवलेंथ निकालना. खैर, तो अकॉर्डिंग टू डी ब्रॉगली इक्वेशन 2.22 ये कहते हैं लैम्डा इज इक्वल टू एच बाई एम वी इज इक्वल टू छक्का पॉइंट छक्का, तो छक्का इंटू 10⁻34 जूल सेकेंड बाई 0.1 kg इंटू 10 मीटर पर सेकेंड, और ये इक्वल टू होता है 6.626 इंटू 10⁻34 मीटर इन जूल इक्वल टू मीटर. जूल इज इक्वल टू इन ब्रैकेट जूल इज इक्वल टू kg मीटर स्क्वायर पर सेकेंड स्क्वायर. अच्छा, तो जूल को हाँ तो ये कैसे आया सीधे मीटर में? तो जूल इज इक्वल टू kg मीटर स्क्वायर पर सेकेंड स्क्वायर, और ऊपर kg कट उठ गया. चलिए ठीक है. प्रॉब्लम 2.13, द मास ऑफ इलेक्ट्रॉन इज 9.1 × 10⁻31 kg if its kinetic energy is 3.0 into 10⁻25 joule. Calculate its wavelength. सॉल्यूशन कह रहा है कि एक इलेक्ट्रॉन दिया हुआ है जिसका मास दे दिया है kg में, और इसका काइनेटिक एनर्जी भी जूल में दे दिया है. इसका वेवलेंथ निकालना है. काइनेटिक एनर्जी मतलब ये मूव कर रहा होगा भाई, इसमें कुछ मूवमेंट हो रहा है, और ये कितना वेट का है ये दे दिया है, तो इसका वेवलेंथ क्या होगा? तो डी ब्रॉगली वेवलेंथ से ही, सॉरी डी ब्रॉगली के फॉर्मूला से निकलने वाला है. 2.2 ही काम आएगा शायद. सिंस kinetic energy is equal to half mv square, तो v is equal to 2 k by m to the whole power 1 by 2 is equal to 2 into 3.0 into 10 to the power 20 minus 25 kg meter square per second square by 9.1 into 10 to the power minus 31 kg to the whole square 1 by 2 is equal to 812 meter per second. Lambda is equal to h by mv is equal to 6.626 into 10 to the minus 34 joule second by 9.1 into 10 to the minus 31 kg into 812 meter per second is equal to 8967 into 10 to the minus 10 meter is equal to 896.7 nanometer. Problem 2.14. Calculate the mass of photon with a wavelength 3.6 एंगस्ट्रोम. बहुत छोटा वेवलेंथ दिया हुआ है. अब इसका मास यानी रिवर्स अब हमको पूछ रहा है. पहले मास और स्पीड दे रहा था, पूछ रहा था वेवलेंथ. अब इसका सिर्फ और सिर्फ वेवलेंथ दिया है जो कि बहुत स्मॉल है. कह रहा है मास बताने के लिए तो लैम्डा इज इक्वल टू 3.6 एंगस्ट्रॉम गिवन इज इक्वल टू 3.6 इंटू 10 टू माइनस 10 मीटर में हो गया. वेलोसिटी ऑफ फोटोन इज इक्वल टू वेलोसिटी ऑफ लाइट. m is equal to h by lambda v is equal to 6.626 into 10 minus 34 joule second by 3.6 into 10 to minus 30 sorry 3.6 into 10 to minus 10 meter in bracket 3 into 10 to 8 meter per second. That will finally give us 6.135 into 10 minus 29 kg. Important बात ये है कि कौन सा फॉर्मूला लगा. मास इज इक्वल टू h by लेम्डा v. ठीक है, v मतलब वेलोसिटी ऑफ फोटोन जो कि वेलोसिटी ऑफ लाइट के बराबर था. ठीक है. तो यहाँ पे स्पीड हम लोग को लग रहा था नहीं दिया है क्वेश्चन में, लेकिन दिया था क्योंकि फोटोन दे दिया है ना. फोटोन का स्पीड तो वही होता है. तो ये सब चीज़ें ध्यान देनी होती है क्वेश्चन में. बहुत आसान है, इसे पूछेगा नहीं, पूछ भी सकता है, बोर्ड के लिए इम्पॉर्टेंट है. 2.5.2 Heisenberg's uncertainty principle. Werner Heisenberg, a German physicist in 1927, stated uncertainty principle, which is the consequence of dual behavior of matter and radiation. It states that it is impossible to determine simultaneously the exact position and exact momentum or velocity of an electron. ये कहते हैं कि ये इम्पॉसिबल है एक साथ हमें किसी भी पार्टिकल का वेलोसिटी और पोजीशन ज्ञात करना. कि आप जब पोजीशन ज्ञात करने जाइएगा तो पता चलेगा वेलोसिटी उसकी इतनी ज़्यादा थी तो पोजीशन कैसे. और आपको अगर वेलोसिटी पता चल गया तो बहुत ज़्यादा हाई वेलोसिटी है तो फिर आपको मतलब सेकेंड का लाख हिस्सा भी कर दीजिएगा. वेलोसिटी बहुत लाख गुना से करोड़ गुना है. आप समझ रहे हैं क्या. तो वो पता नहीं किसी पार्टिकुलर पॉइंट पे उसको देखने जाइएगा तो कहाँ से कहाँ भाग जाएगा. तो इसलिए ये इम्पॉसिबल हो जाता है फॉर द हाई वेलोसिटी पार्टिकल्स. ठीक है ना. तो इसीलिए बोले थे कि इट स्टेट्स दैट इज इम्पॉसिबल टू डिटरमिन साइमल्टेनियसली द एग्जैक्ट पोजिशन एग्जैक्ट मोमेंटम और वेलोसिटी ऑफ एन इलेक्ट्रॉन. मैथमेटिकली इट कैन बी स्टेटेड एज इन इक्वेशन 2.23. कैसे, तो चलिए देखते हैं. 51 नंबर पेज पर हम लोग आ गए हैं. बता दें डेल्टा एक्स इंटू डेल्टा पी एक्स इज ग्रेटर दैन इक्वल टू एच बाई 4 पाई. ये 2.23 हमारा इक्वेशन बन गया. और डेल्टा एक्स इंटू डेल्टा एम वी एक्स इज ग्रेटर दैन इक्वल टू एच बाई 4 पाई, क्योंकि पी एक्स को हम लोग एम वी एक्स लिख सकते हैं. और डेल्टा एक्स इंटू डेल्टा वी एक्स इज ग्रेटर दैन इक्वल टू एच बाई 4 पाई m, where delta x is the uncertainty in position and delta px or delta vx is the uncertainty in momentum or velocity of the particle. If the position of the electron is known with high degree of accuracy, delta in bracket delta x is small, then the velocity of the electron will be uncertain. Delta Vx is large. On the other hand, if the velocity of the electron is known precisely, delta Vx is small, then the position of the electron will be uncertain, delta x will be large. Thus, if we carry out some physical measurements on the electron's position or velocity, the outcome will always depict a fuzzy or blurred picture. The uncertainty principle can be best understood with the help of example. Suppose you are asked to measure a thickness of a sheet of paper with an unmarked meter stick. Obviously, the results obtained would be extremely inaccurate and meaningless. In order to obtain any accuracy, you must use an instrument graduated in units smaller than the thickness of a sheet of paper. Analogously, in order to determine the position of an electron, we must use a meter stick calibrated in units of smaller than the dimensions of the electron. Keep in mind that the electron is considered a point charge and is therefore dimensionless. To observe an electron, we can illuminate it with light or electromagnetic radiation. The light used must have a wavelength smaller than the dimensions of an इलेक्ट्रॉन. आप समझ रहे हैं ना यहाँ पे कितना अच्छा बात इलेक्ट्रॉन के बारे में बताया है कि इलेक्ट्रॉन को हम लोग कोई एक डायमेंशन के रूप में नहीं देख सकते हैं, ठीक है ना. नेचर नो डायमेंशनलेस होता है, लेकिन फिर भी अगर इसको हमको नापना है तो अगर वेव लेंथ इसका कुछ ना कुछ होता है, डायमेंशन नहीं है, तो आप समझ रहे हैं ना, पढ़िए तो समझ में आएगा. इट्स अ वेरी फैंटास्टिक थिंग. और यहाँ पे चीज़ें आसान हो गई है. वी आर जस्ट नियर on the end of the chapter, so keep calm, have patience, have control on your यही कंट्रोल धीरे धीरे आपका आदत बन जाएगा, फितरत बन जाएगा, फिर आप बढ़ चलेंगे एक्सेलेंस की तरफ. तो आग में चलना पड़ता है, पीटना पड़ता है, वही काम हो रहा है. चलिए पीटिए, ठीक है, थकिए, हारिए, टूटिए, घिसिए, थकिए, लेकिन इन सब से आप मरेंगे नहीं, बल्कि संघर्ष करते करते धीरे धीरे मजबूत बन जाएंगे. और फिर इतने मजबूत बन जाएंगे कि आपको ये सारी चीज़ें जिनमें लोग जलते हैं, मरते हैं, रोते हैं, आपको उनमें कोई प्रभाव नहीं पड़ेगा. ठीक, चलिए. जैसे साउथ अफ्रीका के लोग को ज़्यादा गर्मी कैसे फील होगा, वो लोग को गर्मी में ढलने का आदत हो गया है. हमारे यहाँ का लोग रिलेटिवली कम गर्मी में रहा है, वहाँ पे जाएगा तो हाहाकार करने लगेगा. वहाँ का लोग ज़्यादा गर्मी में रहते हैं, यहाँ की कम गर्मी में आएगा तो कहेगा जाए, यहाँ पे तो गर्मी नहीं पड़ रहा है. समझ में आ गया ना, वही बात होता है. तो चलिए यहाँ पे हम लोग लास्ट टॉपिक पे हैं. और द लास्ट, द high momentum photons of such light p is equal to h by lambda would change the energy of electrons by collisions. In this process, we no doubt would be able to calculate the position of the electron, but we would know very little about the velocity of the electron after the collision. Significance of uncertainty principle. One of the important implications of the Heisenberg uncertainty principle is that it rules out existence of definite paths or trajectories of electrons and other similar particles. The trajectory of an object is determined by its location and velocity at various moments. If we know where a body is at particular instant, and if we also know its velocity and forces acting on it at that instant, we can tell where the body would be sometime later. We therefore conclude that the position of an object and its velocity fix its trajectory. For a since for a subatomic object such as an electron, it is not possible simultaneously to determine the position and velocity at any given instant to an arbitrary degree of precision, it is not possible to talk of the trajectory of an electron. The effect of Heisenberg uncertainty principle is significant only for motion of microscopic objects and is negligible for that of a macroscopic objects. This can be seen from the following examples. If the uncertainty principle is applied to an object of mass, say about a milligram, 10 to the power minus 6 kg, then delta V into delta X is equal to h by 4 pi m is equal to 6.626 into 10 to the power minus 34 joule second by 4 into 10 to 4 into 3.1416 into 10 to the power minus 6 kg is approximately nearly equal to 10 to the power minus 28 per meter square per second. तो ये इसकी स्पीड रहेगी. स्पीड कितनी कम हुई आपको समझ में आ रहा है ना. ये सॉरी स्पीड थोड़ी रही, मीटर पर सेकेंड थोड़ी है, पर मीटर स्क्वायर पर सेकेंड है. खैर पता नहीं. वर्नर हाइजेनबर्ग फ्रॉम 1901. ये तो इंडियन की तरह दिख रहे हैं, बूढ़े गोल गोल मुंह वाले. Werner Heisenberg 1901 to 1976. Werner Heisenberg 1901 to 1976 received his PhD in physics from the University of Munich in 1923. He then spent a year working with Max Born at Göttingen, 3 years with Niels Bohr in Copenhagen. He was professor of physics at the University of Leipzig from 1927 to 1914. During World War II, Heisenberg was in charge of German research on atomic bomb. After the war, he was named director of Max Planck Institute for Physics in Göttingen. He was also accomplished mountain climber. Heisenberg was awarded the Nobel Prize in Physics in 1932. यार सबको नोबेल प्राइज मिल गया था क्या. चलिए 52 नंबर पेज. The value of delta V into delta X in velocity or displacement का multiplication obtained is extremely small and is insignificant. Therefore, one may say that in dealing with milligram sized or heavier objects, associated uncertainties are hardly of any real consequence. In case of microscopic objects like an electron, on the other hand, delta V into delta X obtained is much larger and such uncertainties are of real consequence. For example, for an electron whose mass is 9.11 into 10 to the power minus 31 kg, according to Heisenberg's uncertainty principle, delta V into delta X is equal to h by 4 pi m, that is equal to 6.626 into 10 to the power minus 34 joule second by 4 into 3.1416 into 9.11 into 10 to the power minus 31 kg is equal to 10 to the power minus 4 per meter square per second. It is therefore means that if one tries to find the exact location of the electrons, say to an uncertainty to only 10 to the power minus 8 meter, then the uncertainty delta V in velocity would be what would be which is so large. Sorry, would be यहाँ पे कुछ छूट गया है. would be बीच में blank है. I don't know what it is. पता नहीं. Please find friends. Important चीज छूटा रह गया यहाँ पे. So which is so large that the classical picture of the electrons moving in Bohr's orbits fixed cannot hold good. It therefore means that the precise statement of the position and momentum of electrons have to be replaced by the statement of probability that the electron has a given position and momentum. This is what happens in the quantum mechanical model of atom. Okay, now we should solve a problem 2.15. A microscope using suitable photons is employed to locate an electron in an atom within a distance of 0.1 angstrom. What is the uncertainty involved in the measurement of its velocity? Delta solution. Delta X and delta P is equal to h by 4 pi, or delta X m delta V is equal to h by 4 pi. Delta V is equal to h by 4 pi delta x m. Delta V is equal to छक्का पूर्ण छक्का तो छक्का इंटू 10 का पावर माइनस 34 joule second by 4 into 3.14 into 0.1 into 10 to the power minus 10 meter into 9.11 into 10 to the power minus 31 kg is equal to 0.579 into 10 to the power 7 meter per second in bracket 1 joule is equal to 1 kg per meter, sorry, 1 joule equal to 1 kg meter square per second square. And now the next step is equal to 5.79 into 10 to the power 6 meter per second. This will be the speed. Problem 2.16. A golf ball has a mass 40 gram and a speed of 45 meter per second. If the speed can be measured with its accuracy of 2%, calculate the uncertainty in the position. Friends, have a focus on the data given in the question and try to understand along with the reading. देखकर पढ़ते हुए समझते रहिए, कोशिश करिए, धीरे धीरे ये आपकी हैबिट बन जाएगी. जितना तेज पढ़िएगा उतना तेज समझिएगा, इससे फ़ायदे होंगे ना. तभी आपको, जो हम लोग सुनते हैं विवेकानंद जल्दी इतना किताब पढ़ जाते थे, तो वो तो खैर एक अलग फंडा होता था. वो पैराग्राफ देख कर के, जैसे हम लोग एक लाइन को पढ़ने में जितना समय लगाते हैं, वो पैराग्राफ देख कर के पैराग्राफ को लाइन के रूप में इस्तेमाल करते थे. पैराग्राफ देखें, समझ में आ गया पूरे पैराग्राफ में क्या लिखा हुआ है, तो वो एक अलग दृष्टि सेट करनी पड़ती है. वो भी खैर फोकस, कंसंट्रेशन और धीरे धीरे आदत से बनता है. ठीक है, ठीक है. तो वो तो एक दिव्य लक्षण होता है. दैट इज अ ग्रेट एक्सेलेंस दैट नीड्स अ वेरी शॉर्ट ऑफ practice, concentration, focus and much intelligence also. सो मेरे कहने का मतलब था, यहाँ पे गोल्फ बॉल का देखो, वेट दिया हुआ है 40 ग्राम और स्पीड दिया हुआ है 45 मीटर पर सेकेंड. 45 मीटर पर सेकेंड स्पीड बहुत ज़्यादा हुआ, लेकिन इसका मास मात्र 40 ग्राम का गोल्फ बॉल होता है क्या? ये का सबका बात है. अच्छा, द स्पीड कैन बी मेजर्ड विद इन एक्यूरेसी ऑफ 2%, कैलकुलेट द अनसर्टेनिटी इन द पोजिशन. तो सॉल्यूशन, द अनसर्टेनिटी in the speed is 2%, that is 45. 2 by 100 is equal to 0.9 meter per second. Using the equation 2.22, delta x is equal to h by 4 by m, delta v is equal to 6.626 into 10 to the minus 34 joule second by 4 into 10 3.14 into 40 gram into 10 to the power minus 3 kg per gram in bracket 0.9 meter per second finally gives 1.46 into 10 to the power minus 33 meter. This is nearly equal to 10 to the power minus 8. Sorry, this is nearly equal to 10 to the power 18 times smaller than the diameter of a typical atomic ray. एटॉमिक न्यूक्लियस, अरे बाप रे बाप, ये क्या बात है यार. एटॉमिक न्यूक्लियस, देख तो एटम इतना छोटा, उसमें भी एटॉमिक न्यूक्लियस इतना छोटा, उसमें भी उसका 10 का पावर 18 गुना छोटा ये वैल्यू हुआ. क्या बात यार. तो वही है, दिस नियरली इक्वल टू 10 to the power 18 times smaller than the diameter of a typical atomic nucleus. As mentioned earlier, for large particles the uncertainty principle sets no meaningful limit to the precision of the measurements. Reasons for the failure of Bohr model. One can now understand the reason for the failure of Bohr model. In Bohr model, an electron is regarded as a charged particle moving in a well-defined orbit. In a well-defined circular orbits about the nucleus. The wave character of the electron is not considered in Bohr model. Further, an orbit is a clearly defined path, and this path can completely be defined only if the both position and the velocity of the electron are known exactly at the same time. This is not possible according to the Heisenberg uncertainty principle. Bohr model of 100 hydrogen atom therefore not only ignores dual behavior of matter but also contradicts Heisenberg uncertainty principle. In view of properties, it specifies the law of motion that these objects obey quantum mechanics is applied to macroscopic objects for which wave-like properties are insignificant. The results of the same as those from the classical mechanics. Quantum mechanics was developed independently in 1926 by Werner Heisenberg and Erwin Schrödinger. Here, however, we shall be discussing the quantum mechanics, which is based on the idea of wave motion. The fundamental equation of quantum mechanics was developed by Schrödinger and it won him Nobel Prize in Physics in 1933. This equation, which incorporates wave-particle duality of matter, was proposed by de Broglie, is quite complex and knowledge of higher mathematics is needed to solve it. You will learn its solution for different systems in higher classes. For अरे यार फिर हम गड़बड़ हो गया क्या इन द व्यू ऑफ प्रॉपर्टीज सॉरी इन द व्यू ऑफ these inherent weaknesses sorry I have to read this left side of paragraphs but I repeated the same mistake and just continue to the right side directly without having read the left side. So let's study it first. In the last chapter, what was the sequence? In the last page, Bohr model of the hydrogen atom therefore not only ignores dual behavior of matter but also contradicts Heisenberg's uncertainty principle. In the view of the other inherent weaknesses in the Bohr model, there was no point in extending Bohr model to other atoms. In fact, an insight into the structure of atom was needed which could account for wave particle duality of matter and be consistent with Heisenberg's uncertainty principle. This came with the advent of quantum mechanics 2.6 quantum mechanics mechanical model of atom. Classical mechanics based on Newton's law of motion successfully describes the motion of all macroscopic objects such as falling stone or biting planets etc., which have essentially a particle-like behavior as shown in the previous section. However, it fails when applied to microscopic objects like electrons, atoms, molecules, etc. This is mainly because of the fact that classical mechanics ignores the concept of dual behavior of matter, especially for subatomic particles, and the uncertainty principle, the branch of science it takes into account this behavior. This dual behavior of matter is called quantum mechanics. Quantum mechanics is a theoretical science that deals with the study of motions of microscopic objects that have both observable wave-like and particle-like properties. It specifies the law of motion that these objects obey when quantum mechanics is applied to macroscopic objects for which wave-like properties are insignificant. The results are the same as those from the classical mechanics. Quantum mechanics are developed independently in 1926 by Werner Heisenberg and Erwin Schrödinger. Here, however, we shall be discussing the quantum mechanics, which is based on the idea of wave motion. The fundamental equation of quantum mechanics was developed by Schrödinger and it won him the Nobel Prize in Physics in 1933. This equation, which incorporates wave-particle duality of matter as proposed by de Broglie, is quite complex and knowledge of higher mathematics is needed to solve it. You will learn its solutions for different systems in higher classes. For a system such as atom or a molecule whose energy does not change with the time, the Schrödinger equation is written as H psi is equal to E psi. Here H cap is a mathematical operator called Hamiltonian. Schrödinger gave a recipe of constructing this operator from the expression for the total energy of the system. The total energy of the system takes into account the kinetic energy of all the subatomic particles, that is electrons, nuclei, attractive potential between the electrons and nuclei, and repulsive potential between the electrons and nuclei of solutions of these equation gives E and psi hydrogen atom and Schrödinger equation. When Schrodinger equation is solved for hydrogen atom, a solution gives the possible energy levels the electrons can occupy and the corresponding wave functions psi of the electron associated with each energy level. These quantized energy eh, states and corresponding wave functions, which are characterized by a set of three quantum numbers in bracket principal quantum number n, azimuthal quantum number l, and the magical quantum number ml, arise as a natural consequence in the solution of Schrodinger equation. Let's study this thing again, because from this onwards we are entering in a very uh, what everything is important, but a very basic thing that will become the base of further next chapters, and very great, big, and important chapter, chemical bonding. Okay, so you will find the reasons in this only. So let's repeat it also. Repeat it again. However, atom and the Schrodinger equation, when hydrogen atom and the Schrodinger equation. When Schrodinger equation is solved for hydrogen atom, the solution gives the possible energy levels the electron can occupy and the corresponding wave functions psi of the electron associated with each energy level. These quantized energy states and the corresponding wave functions, which are characterized by a set of three quantum numbers, principal quantum number n, azimuthal quantum number l, and magnetic quantum number ml, arise as a natural consequence in the solution of the Schrodinger equation. When an electron is in any energy state, the wave function corresponding to that energy state contains all information about the electron. This wave function is a mathematical function whose value depends upon the coordinates of the electron in the atom and does not carry any physical meaning. Such wave functions of the hydrogen and hydrogen species which one electron are called atomic orbitals. Such wave functions pertaining to one electron species are called one electron systems. The probability of finding an electron at a point within an atom is proportional to the uh, to the in mod psi square psi mod square at that point. The quantum mechanical results of the hydrogen atom successfully predict all the aspects of the hydrogen atom spectrum, including some phenomena that could not be explained by Bohr model. Application of Schrodinger equation to multi-electron atoms presents a difficulty. The Schrodinger equation cannot be solved exactly for a multi-electron atom. This difficulty can be overcome by using approximate methods. Such calculations with the aid of modern computers show that orbitals in atoms other than hydrogen do not differ in any radical way from the hydrogen orbitals discussed above. The principal difference lies in the consequence of increased nuclear charge. Because of this, all the orbitals are somewhat contracted. Further, as you shall see later in subsections 2.6.3 and 2.6.4, unlike orbitals of hydrogen-like species, those energies depend only on the quantum number n. The energies of orbitals in multi-electron atoms depend on quantum numbers n and l. Oh shit. Let's study this once again. We have reached on the 54 page number. Okay, proceeding from the last topic where we were. When an electron is in any energy state, the wave function corresponding to the energy state contains all the information about the electron. The wave function is a mathematical function whose value depends upon the coordinates of the electron in the atom and does not carry any physical meaning. Such wave function of the hydrogen and hydrogen-like species with one electron are called atomic orbitals. Such wave functions pertaining to one electron species are called one electron systems. The probability of finding an electron at a point within an atom is proportional to the mod psi square at that point. The quantum mechanical results of the hydrogen atom successfully predict all the aspects of hydrogen atom spectrum, including some phenomena that could not be explained by the Bohr model. Application of the Schrödinger equation to the multi-electron uh, presents a difficulty. The Schrödinger equation cannot be solved exactly for a multi-electron atom. This difficulty can be overcome by using approximate measures. Some calculations of the aid of modern computers show that orbitals in atom other than hydrogen do not differ in any radical way from the hydrogen orbitals discussed above. The principal difference lies in the consequence of increased nuclear charge. Because of this, all the orbitals are somewhat contracted. Further, you shall see later in subsections 2.6.3 and 2.6.4, unlike orbitals of hydrogen or hydrogen-like species whose energies depend only on the quantum number n, the energies of the orbitals in multi-electron atoms depend on quantum numbers n and l. Okay. Now, important features of the quantum mechanical model of atom. Quantum mechanical model of atom is the picture of structure of atom which emerges from the application of Schrödinger equation to atoms. The following are the important features of the quantum mechanical model. First, the energy of the electrons in atoms is quantized, that is, can only have certain specific values. For example, when electrons are bound to the nucleus uh, in atoms. Second, the existence of quantized electronic energy levels is directly result of wave-like properties of electrons and are allowed solutions of Schrödinger wave equation. Third, both the exact position and exact velocity of an electron in an atom cannot be determined simultaneously. That is Heisenberg's principle. The path of an electron in an atom therefore can never be determined or known accurately. This is why you shall see later on one talks of any probability of finding the electron at different points in an atom. 4. An atomic orbital is the wave function psi for an electron in an atom. Whenever an electron is described by a wave function, we say that the electron occupies that orbital. Since many such wave functions are possible for an electron, there are many atomic orbitals in an atom. These one electron orbital wave functions or orbitals form the basis of the electronic structure of atoms. In each orbital, the electron has a definite energy. An orbital cannot contain more than 2 electrons. In a multi-electron atom, the electrons are filled in various orbitals in the order of increasing energy. For each electron of a multi-electron atom, there shall therefore be an orbital wave function characteristic of orbital it occupies. Wave function characteristic of the orbital it occupies. All the information about the electron in an atom is stored in its orbital wave function psi, and the quantum mechanics makes it possible to extract the information out of psi. बहुत important line है ये. All the information about the electron in an atom is stored in its orbital wave function psi, and quantum mechanics makes it possible to extract this information out of psi. Fifth, the probability of finding an electron at a point within an atom is proportional to the square of the orbital wave function, that is under mod psi square at the point. Under mod psi square is known as probability density and is always positive. From the value of mod psi square at different points within an atom, it is possible to predict the region around the nucleus where electron will most probably be found. 2.6.1 Orbital and quantum numbers. A large number of orbitals are possible in an atom. Qualitatively, these orbitals can be distinguished by their sizes, shape, and orientation. An orbital of same size means there is more chance of finding electron near the
nucleus. Similarly, shape and orientation mean that there is more probability of finding the electron along certain directions than along others. Atomic orbitals are precisely distinguished by what are known as quantum numbers. Each orbital is distinguished by three quantum numbers labeled as n, l, and ml. The principal quantum number n is a positive integer with value n is equal to 1, 2, 3 dash dash dash. The principal quantum number determines the size and to large extent the energy of the orbital. For hydrogen atom and hydrogen like species in bracket He plus comma Li2 plus comma dash dash etc. bracket closed, energy and size of the orbital depends only on n. The principal quantum number also identifies the shell. With the increase in the value of n, the number of allowed orbital increases and are given by n square. All the orbitals of a given value of n constitute a single shell of atom and are represented by the following letters. N is equal to 1, 2, 3, 4 dash dash dash. Shell is equal to KLMN dash dash dash. Size of the orbital increases with the increase of principal quantum number n. In other words, the electron will be located away from the nucleus. Since energy is required in shifting away from the negatively charged electron from the positively charged nucleus, the energy of the orbital will increase with increase of n. Azimuthal quantum number L is also known as an orbital angular momentum or subsidiary quantum number. It defines the three-dimensional shape of the orbital. For a given value of n, L can have n values ranging from 0 to n minus 1. That is, for a given value of n, it is possible value of L is equal to 0, 1, 2 dash 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 n minus 1. For example, when n is equal to 1, a value of L is only 0. For n is equal to 1, the possible values of L can be 0 and 1, and for n is equal to 3, the possible values of L are 0, 1, 2, 0, 1, 2, 0, 1, 2, yes, 0, 1, 2. Each shell consists of one or more subshells and subcells or sublevels. The number of subcells in a principal shell is equal to the value of n. The number of each shell consists of one or more subshells or sublevels. The number of subshells in a principal shell is equal to the value of n. The number of subshells in a principal shell is equal to the value of n. फर्स्ट शेल में एक सब शेल होगा, दो सेकंड शेल में दो सब शेल होगा. इसका मतलब यही होता है. फॉर एग्जांपल द फर्स्ट शेल n is equal to 1, there is only one subshell which corresponds to L is equal to 0. There are two subshells L is equal to 0, 1 in the second cell and 3 L is equal to 0, 1, 2 in the third shell and is equal to 3. सही बात है, and so on. Each subshell is assigned a azimuthal quantum number L. Subcells corresponding to different values of L are represented by the following symbols. Values of L 0, 1, 2, 3, 4, 5. Notation for subshells SPT, FG, H respectively. Table 2.4 shows the permissible values of L for a given principal quantum number and the corresponding subshell notation. Table 2.4 subshell notations. N 1, 2, 3, 4, 1, 2, 2, 3, 3, 4, 4, 4, 4. L is 0, 0, 1, 0, 1, 2, 0, 1, 2, 3. Subshell notation 1s, 2s, 2p, 3p, 3s, 3d, 3, 4s, 4p, 4d, 4f. Again, table 2.4 subshell notations. For n, L is if 0, its subshell notation is 1s. If n is 2, L is 0, subshell notation is 2s. For n2, L1, subshell notation is 2p. For n3, L0, subshell notation will be 3s. For n3, L1, subshell notation is 3p, and for n3, L2, subshell notation 3d, and for L0, subshell notation 4s, N4L1 subshell notation 4p, N4L2 subshell notation 4d, and N4L3 subshell notation 4f. Magnetic orbital quantum number ml gives information about the spatial or orientation of the orbital with respect to the standard set of coordinate axes for any subshell defined by L value to L plus 1 values of ml are possible, and these values are given by ml is equal to minus L minus 1 minus L minus 2 dash 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 0 1 dash dash L minus 2 L minus 1 L. Thus, for L is equal to 0, the only permitted value of ml is equal to 0. 2 because 2 into 0 plus 1 is equal to 0, 1 s orbital. For L is equal to 1, ml can be minus 1 0 and plus 1. Okay, 3 p orbitals. For L is equal to 2, ml is equal to minus 2 minus 1 0 plus 1 and plus 2. In bracket 2 into 2 plus 1 is equal to 5 d orbitals. It should be noted that the value what it told 5d orbitals. What is it? What is it, friend? What it is? What is it? Yes, over here. Thus, for L is equal to 0, the only permitted value of ml is equal to 0 is the 1s orbital. For L is equal to 1, ml can be minus L 0 and plus 1 is equal to 3, that is 3 p orbitals. And if L is equal to 2, ml is equal to minus 2 to plus 2 in between, there will be 5 d orbitals. It should be noted that the values of ml are derived from L and that the values of L are derived from N. Each orbital in an atom therefore is defined by a set of values of N, L and ml. N orbital described by the quantum numbers n is equal to 2, L is equal to 1, ml is equal to 0 is an orbital in the p subshell of the second shell. P subshell of the second shell. The following chart gives the relation between the subshell and the number of orbitals associated with this value of L 0 1 2 3 4 5. Subshell notation as B D F G H. Number of orbitals 1 3 5 7 9 11. That's very simple. Electron spin has the 3 quantum numbers labeling an atomic orbital can be used equally well to define its energy, shape and orientation. But all these quantum numbers are not enough to explain the line spectra observed in case of multi-electron atoms. That is, some of the line actually occurs in doublets, in bracket 2 lines closely spaced, triplets 3 lines closely spaced. This suggests the presence of a few more energy levels than predicted by the 3 quantum numbers. In 1925, George Olin Block and Samuel Goudsmith propose the presence of fourth quantum number known as electron spin quantum number ms. An electron spins around its own axis much in a similar way as Earth spins around its own axis while revolving the Sun. In other words, an electron has, besides charge and mass, intrinsic spin, angular quantum numbers, spin, angular momentum, and electron, a vector quantity, can have two orientations relative to the chosen axis. These two orientations are distinguished by the spin quantum numbers ms, which can take the values of plus half or minus half, and these are called the two spin states of the electron and are normally represented by the arrows spin up and down arrow, that is spin down. The two electrons that have different ms values, one plus half and other minus half, are said to have opposite spins. An electron, an orbital, cannot hold more than two electrons, and these two electrons should have opposite spins. To sum up these, okay, to sum up these four quantum numbers, provided that there are some to sum up four quantum numbers, provide the following information. First, n defines the shell, determines the size of orbital and also a large extent energy of the orbital. Second, there are n subshells in a nth shell. L identifies the subshell and determines the shape of the orbital. See section 2.6.2. Where is section 2.6.2? Where is section 2.6.2? Section 2.6.3 it is. Okay, where we will go here. 2.6.2. okay, first let us complete this now. To sum up, the four quantum numbers provide the following information. First, n defines the shell, determine the size of the orbital and also to a large extent the energy of the orbital. Second, there are n subshells. In the nth shell, L identifies the subshell and determines the shape of the orbital. See figure 2.6.2. There are 2l plus 1 orbitals and each type in a subshell. That is 1s orbital, L is equal to 0, 3p orbitals, L is equal to 1, and 5d orbitals, L is equal to 2 per subshell. To some extent, L also determines the energy of the orbital in a multi-electron atom. Third, ML designates and designates. ML designates the orientation of the orbital for a given value L. ML has 2l plus 1 values, the same as the number of orbitals per subshell. It means that the number of orbitals is equal to the number of ways in which they are oriented. Fourth, ms refers to the orientation of the spin of the electron. I didn't understand what does this orientation of the spin means. So can I repeat this electron spin as? Of course, please give me permission. If you don't like, skip it further. Sorry for the inconvenience caused to you. क्षमा चाहूँगा. चलिए दोबारा पढ़ते हैं इलेक्ट्रॉन स्पिन s को. The three quantum numbers labeling an atomic orbital can be used well to define its energy, shape, or orientation, but all these quantum numbers are not enough to explain the line spectra observed in case of multi-electron atoms. There is some of the lines actually occur in doublets. Two lines closely spaced replace three lines closely spaced. This suggests that presence of one few more energy levels than predicted by three quantum numbers. In 1925, George Bloch and Samuel Goudsmith proposed the presence of fourth quantum number known as electron spin quantum number ms. The electron spin around its own axis, which is similar as
Earth spin around its own axis while revolving around the sun. In other words, an electron has, besides charge and mass, intrinsic spin angular quantum number. Spin angular quantum number of the electron or vector quantity has two orientations relative to the chosen axis. Then two orientations are distinguished by spin quantum numbers ms, which can make the values of plus half and minus half, and these are called the two spin states of the electron. इसके बाद तो अपन को समझ में आई क्या है प्लस हाफ और माइनस हाफ होता है। दो तरीके के स्पिन को स्पिन अप स्पिन डाउन से रिप्रेजेंट करते हैं कैन नॉट हैव, और एक ऑर्बिटल में दो स्पिन ही रह सकते हैं जो कि दोनों को अपोजिट ही होना पड़ेगा। इस टॉपिक को समझने के लिए हमको लगता है कि हम क्वांटम जो है ये कुछ क्वांटम चीज़ को अच्छे से समझे नहीं है। ठीक है, क्वांटम, व्हाट इज दिस क्वांटम? क्वांटम क्वांटम केमिस्ट्री, क्वांटम मैकेनिक्स, क्या कहा जाए इसको, कि इधर है क्वांटम द प्रिंसिपल सब्सिडियरीज quantum numbers and the energies of the multi-electron quantum numbers and application of Schrödinger। यही तो अच्छे से नहीं समझा है, बहुत गलत किया है। quantum numbers, the branch of science that takes into quantum mechanical model of atom। इस टॉपिक को जरा थोड़ी देर पढ़ते हैं। classical mechanics based on successfully describe motion macroscopic, तो NLM जो है मैक्रोस्कोपिक ऑब्जेक्ट, लेकिन दूसरे छोटे इलेक्ट्रॉन्स मॉलिक्यूल्स पर डिपेंड उसका रूल फॉलो नहीं करता है, क्योंकि ये ड्यूअल बिहेवियर को फॉलो करने वाले हैं। और ठीक है, और इसमें तो अनसर्टेनिटी प्रिंसिपल भी आता है। द ब्रांच ऑफ साइंस दैट टेक्स इनटू अकाउंट द ड्यूअल बिहेवियर ऑफ मैटर इज कॉल्ड। ठीक है, तो साइंस का वो ब्रांच जो ड्यूअल बिहेवियर ऑफ मैटर पे स्टडी करता है, ठीक है, द ब्रांच ऑफ इट टेक्स इनटू अकाउंट, तो उसको बोलते हैं क्वांटम मैकेनिक्स। क्वांटम मैकेनिक्स इज द थ्योरेटिकल साइंस दैट डील्स विद द स्टडी ऑफ मोशंस ऑफ द माइक्रोस्कोपिक ऑब्जेक्ट्स दैट बोथ ऑब्जर्वेबल। ठीक है, तो ये क्वांटम मैकेनिक्स और वो न्यूटन मैकेनिक्स जो था, न्यूटन बड़ा के लिए, क्वांटम छोटे छोटे के लिए, मोस्ट पार्टिकल लाइक। ठीक है, क्वांटम मैक्रोस्कोपिक ऑब्जर्व्ड। ठीक है, ओके, तो अब हमें आना चाहिए नीचे। अच्छा, थोड़ा सा और क्या था यहाँ पे, मैकेनिकल मॉडल,